For centuries, humanity has gazed at the stars, yearning for answers to our most profound questions. Yet with each new discovery, we uncover even greater mysteries. From the mind-bending physics of black holes to the tantalizing possibility of ancient alien visitors, our universe is a vast expanse filled with enigmas that challenge our very understanding of reality. These mysteries don't just push the boundaries of knowledge, they redefine them, sparking endless curiosity and debate. So join us as we dive into some of the most mind-blowing questions about the universe. When information, matter, or energy falls into a black hole, we encounter one of the most perplexing paradoxes in modern physics. Picture this: a particle carrying intricate details about its properties, its position, speed, and other unique qualities, crosses the event horizon, the point beyond which nothing, not even light, can escape. As it crosses, all the information that once defined that particle seems to vanish from our observable universe. This raises a fundamental question. Can information truly disappear from existence? The laws of quantum mechanics assert that information should never be lost. Yet, the behavior of black holes appears to contradict this principle, posing a challenge to our understanding of both gravity and quantum mechanics. This apparent destruction of information in black holes has become known as the information paradox. Renowned physicist Stephen Hawking once proposed that information falling into a black hole could indeed be lost forever. However, this idea directly conflicts with the principle of quantum determinism, which holds that the past and future states of a system should always be deducible from its present state. Recently, groundbreaking theories, including developments in string theory and the holographic principle, have proposed potential solutions to this paradox. One idea is that information may not be lost, but instead encoded on the event horizon itself, much like a hologram, preserving the details without actually storing them within the black hole. Another fascinating concept involves Hawking radiation, where black holes emit radiation over time and eventually evaporate. Some scientists hypothesize that through this radiation, information might gradually leak out, albeit in a highly scrambled and incomprehensible form. This interplay between quantum mechanics and general relativity continues to be one of the deepest and most perplexing mysteries in physics. Each new step forward in understanding black holes not only sheds light on these cosmic objects, but also brings us closer to unraveling the foundational laws of the universe itself. At the very heart of most galaxies lies an enigma of colossal proportions, the supermassive black hole. These immense giants, with masses ranging from millions to billions of times that of our sun, continue to mystify scientists. How did they come to exist? What forces shaped their enormous size? The formation of supermassive black holes remains a topic of active research, and several theories compete to explain their origins. One of the leading hypotheses suggests that these cosmic behemoths began as smaller, intermediate mass black holes. Over cosmic timescales, they grew by relentlessly consuming gas, dust, and even entire stars from their surroundings. This process, known as accretion, slowly built up their size, while mergers between black holes fueled their growth further, creating an ever-expanding gravitational pull that reached across the galaxy. Another theory posits that the seeds of supermassive black holes were planted very early in the universe's history, just a few 100 million years after the Big Bang. In these primordial conditions, giant clouds of gas could have collapsed directly into large black holes, bypassing the usual smaller stellar black hole phase. This process, often referred to as direct collapse, may explain why supermassive black holes appeared so early in the universe's existence. The merging of galaxies also plays a pivotal role in the growth of these giants. When two galaxies collide, their central black holes can eventually merge, forming an even larger, more massive black hole. As the galaxies merge, vast amounts of gas are drawn toward the newly formed black hole, providing fuel that accelerates its growth. Over billions of years, these supermassive black holes have shaped the galaxies around them, influencing star formation and dictating the dynamics of galactic cores. Understanding how these titans of gravity form and evolve not only offers profound insights into the nature of black holes themselves, but also into the very structure and evolution of the universe. As we continue to uncover the secrets of the universe, one thing becomes clear. The more we discover, the more we realize how much we have yet to understand. These cosmic mysteries, from the paradoxes of black holes to the formation of the largest structures in the cosmos, challenge us to rethink the laws that govern our reality. Yet, with every new breakthrough, we come closer to the answers. Hawking radiation, a concept first proposed by the renowned physicist Stephen Hawking in the 1970s, represents a monumental breakthrough in our understanding of black holes and the universe at large. This theory brought together the seemingly incompatible realms of quantum mechanics and general relativity, introducing an idea so extraordinary that it forever altered the way we think about the cosmos. In a universe where we once believed that nothing could escape the event horizon of a black hole, Hawking's insight revealed that over incredibly long timescales, black holes can in fact emit radiation, leading to their eventual evaporation. But how does this work? The quantum mechanical world is one of constant fluctuation, where particle-antiparticle pairs spontaneously form and annihilate in the vacuum of space. Even near the event horizon of a black hole, where space and time become distorted, these pairs can form and behave in unexpected ways. The intense gravitational forces present near the black hole can sometimes cause one of these particles to fall into the black hole while the other escapes. The escaping particle carries with it a small amount of energy, effectively reducing the black hole's mass. This emission of energy, detectable as Hawking radiation, represents the gradual loss of mass from the black hole. Over time, this process, known as black hole evaporation, continues, slowly shrinking the black hole until it vanishes, though for most large black holes, this process will take longer than the current age of the universe. However, the situation is quite different for smaller black holes. These objects, which have less mass, lose energy more quickly, and as they shrink, the rate of mass loss accelerates. In the end, this rapid loss of mass leads to a final burst of radiation before the black hole disappears entirely. While black hole evaporation might seem like a slow and distant process, it opens a fascinating new pathway for understanding the deeper connections between quantum mechanics, which governs the smallest particles, and Einstein's theory of general relativity, which governs the largest structures in the universe. Now, moving from the microscopic to the cosmic scale, there is another captivating aspect of black hole physics: the potential to harness energy from rotating black holes. These curved black holes, also known as Kerr black holes, carry an enormous amount of rotational energy. Though it may sound like science fiction, tapping into the energy of these rotating giants is rooted in real theoretical physics. In the 1960s, physicist Roger Penrose proposed the Penrose process, a theoretical mechanism that could extract energy from a black hole's rotation. According to the Penrose process, a particle entering the ergosphere, a region just outside the event horizon where space-time is dragged around by the black hole's rotation, could split into two parts. One part would fall into the black hole while the other escapes. In this way, the escaping particle would carry away more energy than the original particle, effectively extracting a fraction of the black hole's rotational energy. This groundbreaking theory suggests that, in principle, we could harness energy from black holes, though such an achievement is far beyond our current technological capabilities. Another exciting possibility comes from the Blandford-Znajek process, which involves the interaction of magnetic fields with the black hole's rotation. This process suggests that the black hole's magnetic field could channel energy in the form of powerful electromagnetic radiation. These energetic jets of particles, which we observe emanating from supermassive black holes at the centers of galaxies, might be the result of such energy extraction mechanisms. Though these theories are tantalizing, the practical challenges involved in harnessing black hole energy are immense. The extreme conditions and vast scales make the actual extraction of energy seem like an impossible engineering feat, at least for now. But even if we are far from building black hole power plants, the study of these processes is invaluable. It deepens our understanding of black holes and the fundamental forces at play at the outer edges of our scientific comprehension. As we venture deeper into the mysteries of black holes, one question lingers in the mind: what would happen if you were to fall into one? The answer depends on the size and mass of the black hole. If you fell into a stellar mass black hole, which is only a few times the mass of our sun, your journey would be violent and incredibly brief. The tidal forces caused by the black hole's immense gravity would stretch and compress your body in a process known as spaghettification. In the end, you would be torn apart long before you reached the event horizon. However, falling into a supermassive black hole, millions or even billions of times the mass of the sun, could be a different experience. The distance from the event horizon to the singularity, the point where gravity crushes all matter to an infinitely dense point, is much greater. As a result, the tidal forces at the event horizon would be much less intense. It's theoretically possible that you could pass through the event horizon without immediate spaghettification, though the journey would still be a perilous one. As you fall deeper into the black hole, your view of the outside universe would shrink to a tiny bright spot above you, slowly fading as you approach the singularity. Once inside the event horizon, the laws of physics as we know them break down. Time and space become intertwined, and the usual rules no longer apply. Theories suggest that you might encounter the singularity itself, where matter is crushed to a point of infinite density, ending your journey. Alternatively, some hypotheses speculate that falling into a black hole might allow you to travel through a wormhole, an exotic, cosmic pathway that could connect distant regions of the universe, potentially even other universes. While these ideas remain speculative, they challenge our understanding of reality and push the boundaries of what we think is possible. Whether you meet your end at the singularity or pass through a wormhole, falling into a black hole represents a journey to the unknown, a final, mysterious voyage into the heart of the universe's most enigmatic entities. In our endless pursuit of knowledge, one of the most exciting and challenging frontiers of modern science lies in detecting exoplanets, planets that orbit stars beyond our solar system. These distant worlds, shrouded in mystery, are revealed through several ingenious techniques, each tapping into different facets of astronomy to unveil their secrets. As we venture deeper into this unknown territory, the quest to understand exoplanets brings with it not only groundbreaking discoveries, but also a renewed sense of wonder about our place in the cosmos. One of the most widely used and highly successful methods in exoplanet discovery is the transit method. This technique relies on the slight, periodic dimming of a star's light when an exoplanet passes directly between us and its parent star. During this transit, the planet casts a shadow that causes the star's brightness to decrease momentarily. By meticulously measuring these dips in brightness, astronomers can infer not just the presence of the exoplanet, but also its size, and even gather preliminary data on its atmosphere. This method, although seemingly simple, has proven to be one of the most effective ways to uncover hidden worlds in distant star systems. Another powerful technique, the radial velocity method, also known as the Doppler method, works by detecting tiny wobbles in a star's position caused by the gravitational pull of an orbiting exoplanet. As the planet orbits its star, it exerts a gravitational tug, causing the star to move slightly towards and away from us. This movement shifts the star's light spectrum toward the blue end when it moves towards us, and toward the red end when it moves away. By studying these spectral shifts, scientists can calculate the exoplanet's mass and determine the length of its orbit. This method, often used in conjunction with others, has provided critical insights into the properties of exoplanets across the galaxy. Direct imaging, though a challenging method, takes a bold approach by attempting to capture actual images of exoplanets. To block out the overwhelming glare of the parent star, astronomers use advanced instruments like coronagraphs or star shades to isolate the faint light reflected or emitted by the exoplanet. This technique is especially useful for studying larger exoplanets located farther from their parent stars, where the contrast between the planet's light and that of its star is more manageable. By capturing these faint images, astronomers are able to gain unprecedented insights into the size, composition, and even the atmospheric characteristics of exoplanets. One of the most intriguing methods, gravitational microlensing, takes advantage of the warping of space-time caused by a massive object, such as a star or planet, passing in front of a more distant star. The gravitational field of the intervening object acts as a lens, magnifying the light from the background star in a specific pattern. If an exoplanet is part of the intervening system, its presence can be inferred from the distinct characteristics of the light curve. This technique has revealed some of the most distant and elusive exoplanets in the universe, providing a unique window into the vast expanse of space. These diverse methods, often used in combination, have led to the discovery of thousands of exoplanets, that each one adding another piece to the puzzle of our understanding of the universe. As we continue to refine our tools and techniques, our ability to detect and study these distant worlds will only grow, allowing us to uncover even more about the nature of planets that orbit stars beyond our own solar system. Among the many discoveries, super-Earths stand out as particularly intriguing. These exoplanets, which are larger than Earth but smaller than the gas giants like Uranus and Neptune, offer a unique glimpse into the process of planetary formation. Super-Earths typically have masses ranging from 1 to 10 times that of Earth, and their composition can vary widely, from rocky planets with thin atmospheres to water worlds with vast, deep oceans. What makes super-Earths so captivating is their potential similarity to Earth. Many of these planets lie within their star's habitable zone, the region where conditions might be just right for liquid water to exist on the surface, an essential ingredient for life as we know it. The study of super-Earths opens the door to exploring planets that might one day harbor life or reveal conditions vastly different from what we experience on Earth. As scientists delve deeper into the study of super-Earths, they're not just exploring potential habitats for life, but also unraveling the mysteries of planetary formation. Our own solar system, for example, lacks planets that sit between the sizes of Earth and Neptune. Thus, the discovery of super-Earths in other star systems helps fill crucial gaps in our understanding of planetary evolution and provides new perspectives on how planetary systems form and evolve. Moreover, some super-Earths have yielded fascinating clues about their atmospheres. By analyzing the light that filters through these planets' atmospheres during transits, astronomers can detect the presence of gases like hydrogen, helium, and even more complex molecules. Studying these atmospheres could help scientists learn more about the processes shaping these worlds, including volcanic activity, weather patterns, and even potential biosignatures, signs of biological processes that could hint at the presence of life. Rogue planets, or nomadic planets, present another layer of intrigue. These planets drift through the galaxy, unbound by any star, wandering in the vast darkness between stars. While the absence of a parent star presents significant challenges for sustaining life, some theoretical scenarios suggest that life might still be possible in these isolated environments. Rogue planets might retain enough internal heat from their formation or experience tidal heating from interactions with a large moon, possibly allowing them to harbor subsurface oceans beneath thick layers of ice. Similar to the icy moons of Jupiter and Saturn, these oceans could potentially support microbial life or even more complex organisms that exploit the energy from hydrothermal vents at the ocean floor. Other rogue planets might possess thick atmospheres rich in hydrogen or insulating gases, which could trap enough heat to sustain liquid water on the surface or beneath an icy shell. This atmospheric insulation could create habitable conditions despite the planet's isolation from a star. Such planets challenge our understanding of habitability and broaden the scope of where life might exist in the universe. In the search for biosignatures, indicators of life, scientists use advanced tools like spectrometers and direct imaging instruments to study exoplanets from light years away. By analyzing the light that filters through a planet's atmosphere or reflecting off its surface, astronomers can detect the presence of gases like oxygen, methane, and ozone, which on Earth are associated with biological activity. The detection of these gases, particularly in specific combinations, could point to the presence of life forms, much like the way the combination of oxygen and methane in Earth's atmosphere is largely produced by living organisms. As our detection methods and technologies continue to evolve, the hunt for exoplanets will not only yield more surprises, but will also deepen our understanding of life's potential beyond Earth. The more we discover, the more we realize that the universe is full of endless possibilities. each discovery a stepping stone toward answering the most profound questions about our place in the cosmos. In the vast, unexplored realms of space, scientists are increasingly focused on detecting technosignatures, which are potential signs of advanced technology. These could include light patterns or radio signals unlike anything we've seen before, signals that echo the emissions from our own technology. However, the search for technosignatures is still a speculative endeavor, with numerous challenges to overcome. Despite these obstacles, the potential discovery of such signals would be a monumental breakthrough, providing the first clear evidence of intelligent life elsewhere in the universe. Groundbreaking missions like the Kepler Space Telescope and the James Webb Space Telescope, along with upcoming projects, could use these methods to explore the atmospheres and surfaces of exoplanets. As our technology advances, so does our ability to detect even the faintest signs of life, bringing us ever closer to answering the profound question, are we alone in the universe? With each new discovery, the dream of finding extraterrestrial life transitions from a speculative idea to the edge of scientific reality, making the search for biosignatures an exhilarating and awe-inspiring journey into the unknown. One of the most compelling mysteries surrounding this search is the Fermi paradox, a puzzle that asks, where is everybody? This paradox, named after physicist Enrico Fermi, is the contradiction between the high probability of extraterrestrial civilizations existing elsewhere in our galaxy and the complete absence of evidence or contact with them. Given the vast number of stars and potentially habitable planets in the Milky Way, the question seems even more perplexing. The Milky Way alone is home to about 100 billion stars, many of which are orbited by planets that could support life. Statistically, it seems likely that intelligent life should be common, yet we have found no conclusive proof of extraterrestrial civilizations. To solve this paradox, several hypotheses have emerged. One such theory is the concept of the Great Filter, a hypothetical stage in the evolution of life that is incredibly difficult to pass. This filter could be in our past, meaning that intelligent life rarely evolves into complex organisms, or it could lie ahead, suggesting that advanced civilizations often self-destruct before they can achieve interstellar communication. Either scenario presents sobering implications for humanity's future. Another theory is the zoo hypothesis, which suggests that advanced extraterrestrial civilizations might be deliberately avoiding contact with us, observing us from afar like animals in a zoo, waiting for us to reach a certain level of technological or ethical maturity. Some also propose that interstellar travel or communication is inherently difficult or resource-intensive, making it challenging for advanced civilizations to spread or be detected. Additionally, it's possible that extraterrestrial life forms are so radically different from life on Earth that we fail to recognize the evidence simply because it doesn't match our expectations. The Fermi paradox remains an open question, one that drives both scientific exploration and speculative thought. Whether the solution lies in biology, technology, or sociology, each theory brings us closer to understanding our place in the cosmos and the potential existence of others who share it. Another intriguing mystery in the universe is the Great Attractor, a gravitational anomaly located in intergalactic space, about 150 to 250 million light-years away in the direction of the Centaurus constellation. This region, part of the Laniakea supercluster, is a vast collection of over 100,000 galaxies bound together by gravity. The Great Attractor's most fascinating feature is its immense gravitational pull, which is drawing entire galaxies toward it at astonishing speeds, up to several hundred kilometers per second. In fact, even our own Milky Way galaxy is being pulled toward this point at a rate of approximately 600 kilometers per second. The exact nature of the Great Attractor is still unclear because it lies within the zone of avoidance, a part of the sky obscured by the dense plane of our own Milky Way, filled with stars, dust, and gas. This makes direct observation extremely difficult. However, advanced observational techniques such as X-ray astronomy have allowed scientists to peer through the dense material, providing new insights into this mysterious phenomenon. Research suggests that the Great Attractor is likely a major supercluster of galaxies, dark matter, and hot gas that generates its intense gravitational field. One of the key structures associated with the Great Attractor is the Norma Cluster, a massive collection of galaxies situated near the center of this gravitational anomaly. Despite these findings, the full extent of what makes up the Great Attractor remains an active subject of study. Understanding this mysterious force not only sheds light on the motion of galaxies in our local cosmic neighborhood, but also helps us understand the larger scale structure of the universe itself. In the vast expanse of the cosmos, a profound and intricate force shapes the universe: gravity. It governs the movement and distribution of galaxies across staggering distances, sculpting the very structure of space. One of the most fascinating features of the universe are cosmic voids, vast, empty regions stretching across millions of light years. These voids, though seemingly barren, are key to understanding the large-scale architecture of the cosmos. They exist as the spacious gaps in between dense clusters and filaments, resembling a web of celestial threads woven together by the gravitational pull of dark matter. The origins of cosmic voids trace back to the aftermath of the Big Bang. In the early universe, particles and energy existed in a nearly uniform state. Over time, tiny fluctuations in the density of matter began to grow, driven by gravitational attraction. Regions with slightly higher densities drew in more matter, eventually forming galaxies and clusters. On the other hand, the less dense regions lost their matter to the denser areas, giving birth to the vast, empty voids we observe today. The expansion of the universe continues to shape this dynamic, with gravity playing a fundamental role in the formation and expansion of these voids. Though it may appear empty, a closer look at the voids reveals something far more complex. Inside these regions, low-density gas, traces of dark matter, and a handful of galaxies can be found. However, these galaxies are vastly different from those in denser regions. They tend to be smaller, dimmer, and more isolated, giving them distinct evolutionary paths. The study of these isolated galaxies is crucial, as it offers valuable insights into how galaxies form and evolve in environments vastly different from the rich, dense cosmic filaments. Cosmic voids also present a unique opportunity to study the mysterious force that drives the accelerated expansion of the universe: dark energy. These under-dense regions react more sensitively to dark energy, making them natural laboratories for scientists seeking to understand this enigmatic force. Despite their emptiness, voids contain vital clues about the universe's past, its ongoing evolution, and the hidden forces that shape its destiny. Galaxies do not exist in isolation. Instead, they are part of an even larger cosmic structure, the galaxy filaments. These massive, thread-like structures extend across hundreds of millions of light years, connecting clusters and superclusters of galaxies in a complex web that spans the entire universe. These filaments are some of the largest known structures in existence and form the backbone of the universe's large-scale architecture. The formation of galaxy filaments began soon after the Big Bang. Tiny fluctuations in the primordial matter distribution set off a chain reaction as gravity pulled matter into increasingly dense regions. Over time, these dense regions formed long, narrow filaments that stretch across the cosmos, linking galaxy clusters together. At the core of these filaments lies dark matter, an invisible substance that serves as the framework around which visible matter accumulates. Galaxies within these filaments follow the dense trails created by dark matter, and their movement is driven by gravitational forces. These cosmic filaments do more than just connect galaxies. They also play a critical role in galaxy formation and evolution. As galaxies move along these filaments, they interact with each other, merging and triggering new waves of star formation. The gravitational forces within these filaments can cause galaxy mergers, ultimately giving rise to even larger structures known as superclusters. The interactions within these filaments are essential for understanding the evolution of galaxies and the universe itself. By mapping these filaments, astronomers can trace the distribution of dark matter, which is a primary force shaping the structure of the cosmos. The study of galaxy filaments reveals how matter is distributed throughout the universe, offering crucial insights into its composition and underlying forces. These observations help us understand not only the formation of galaxies, but also the broader evolution of the universe on a massive scale. In the end, cosmic voids and galaxy filaments are more than just features of the universe's structure. They are windows into the forces that shape the cosmos. Together, they form a vast, intricate system governed by gravity, dark matter, and dark energy, all of which continue to define the universe's evolution across billions of years. Exploring the vast and mysterious structures within the universe, scientists continue to delve deeper into the dynamics of galaxies and the formation of galaxy filaments. These filaments are not merely strands of matter, but serve as fundamental components of the grand structure of the universe, revealing the interplay of matter and gravity that guides the evolution of cosmic landscapes. As we analyze these intricate web-like features of the cosmos, they illuminate how gravitational forces shape and orchestrate the distribution of matter, leading to the formation of galaxy clusters, superclusters, and massive voids that dominate our cosmic environment. These galaxy filaments are a stunning testament to the universe's immense scale and complexity. They span vast stretches of space, weaving together distant galaxies into interconnected webs. Their existence underscores the influence of gravity over immense distances, helping us understand how the universe's architecture took shape. From the Big Bang's earliest moments to the present day, galaxy filaments continue to evolve as cosmic forces draw galaxies together, forming colossal superstructures that stretch across hundreds of millions of light years. This cosmic tapestry, created by gravity's persistent pull, provides insights into the formation of galaxy clusters, which in turn evolve into larger superclusters, such as the Virgo supercluster, which houses our own Milky Way. The journey of supercluster formation begins with tiny fluctuations in the density of matter shortly after the Big Bang. These early variations, remnants of quantum fluctuations, began as tiny, denser pockets of matter scattered throughout the universe. Over time, the force of gravity caused these pockets to attract more material, slowly building into massive clusters of galaxies. These clusters, interconnected by filaments of less dense matter, began to merge over billions of years, resulting in the formation of massive superclusters. These monumental structures continue to evolve under the influence of gravity as galaxy clusters within them move toward one another, colliding and merging to form even denser and more massive clusters. As galaxy clusters collide and merge, new waves of star formation are triggered, altering the shapes and properties of galaxies. Supermassive black holes grow at the centers of galaxies, further altering their evolution. These cosmic interactions not only reshape galaxies, but also highlight the dynamic nature of the universe. Additionally, the expansion of the universe plays a significant role in the evolution of superclusters. As space stretches, some structures become more isolated, drifting farther apart from one another. Tools like large-scale galaxy surveys allow astronomers to map these vast structures, providing a 3D view of the universe's intricate web of galaxies, clusters, and voids. One of the most intriguing mysteries of the universe is the phenomenon known as dark flow. This peculiar motion of galaxy clusters moving in a specific direction contrary to expectations has baffled scientists for years. It was first detected through observations of the cosmic microwave background radiation, the afterglow of the Big Bang. Some galaxy clusters appear to be moving towards a particular point in the sky, a motion that cannot be explained by gravitational influences from known cosmic structures like superclusters or filaments. The existence of dark flow suggests the possibility of forces beyond the observable universe that are affecting the motion of these galaxy clusters. This enigmatic motion challenges our understanding of cosmology, as it suggests there may be influences beyond our cosmic horizon, the furthest distance from which light has had time to travel since the universe's birth. Some theories speculate that dark flow could be caused by massive structures or even other universes exerting their gravitational pull on our observable universe. This possibility pushes the boundaries of known physics, encouraging cosmologists to expand their understanding of the cosmos and consider the existence of multiversal realms that could exist beyond our perception. As scientists continue to investigate dark flow, the potential for groundbreaking discoveries grows, promising to reveal more about the true nature of the universe and its mysterious origins. Additionally, the universe is home to even more extreme and extraordinary phenomena. Hypernovae, the cataclysmic explosions of massive stars, offer a glimpse into the universe's most powerful events. These explosions are far more energetic than typical supernovae, with energy releases up to 100 times greater. Hypernovae result from the collapse of stars at least 30 times the mass of our sun. When these colossal stars exhaust their nuclear fuel, their cores collapse under the immense pressure of gravity, resulting in a release of energy so powerful that it outshines entire galaxies. What distinguishes hypernovae from regular supernovae is their incredible energy output. In a typical supernova, the collapse of the star's core often leads to the formation of a neutron star. However, in a hypernova, the collapse may result in the creation of a black hole instead. Hypernovae are also known for their association with long-duration gamma-ray bursts, some of the brightest electromagnetic events in the universe. These bursts are thought to originate from jets of particles moving at nearly the speed of light, emitted from the poles of the collapsing star. These high-energy phenomena are not only awe-inspiring, but provide valuable clues about the nature of stellar evolution and the extreme conditions that govern the cosmos. In conclusion, these cosmic phenomena, whether it's the intricate web of galaxy filaments, the formation of superclusters, the mystery of dark flow, or the cataclysmic hypernovae, offer us a deeper understanding of the universe's vast and dynamic nature. As our technological capabilities continue to advance, the mysteries of the cosmos will undoubtedly unfold, revealing even more about the forces that shape our universe and the incredible events that have marked its evolution. The study of these phenomena provides us with crucial insights into the fundamental workings of the universe, from its origins to its future. In the vast expanse of the universe, hypernovae stand as colossal cosmic events that play an indispensable role in the formation of the very fabric of matter. During these incredible explosions, elements heavier than iron are forged in the heart of the dying stars, and then, through violent dispersal, they are scattered across space. This process not only enriches the surrounding environment, but also sets the stage for the birth of new stars and planetary systems. The aftermath of hypernovae forms a crucial part of the cosmic cycle, embedding these stellar giants as the essential architects of the universe's evolution. While supernovae contribute to this cycle in a similar manner, the scale of hypernovae is far more intense, marking them as the supreme agents of creation, leaving an indelible impact on the universe's expansive tapestry of matter and energy. As a result of these monumental explosions, heavy elements like gold, uranium, and platinum are spread across space, forming the building blocks for the creation of stars, planets, and even life itself. Hypernovae are not only destructive, they are creative forces that shape the very destiny of galaxies, enabling the creation of complex cosmic structures. The amount of energy released in these events is so immense that it forces the surrounding space to reshape, ensuring that each explosion has a lasting legacy in the cosmic ecosystem. Magnetars, on the other hand, are born from the violent deaths of massive stars and are known for generating the most powerful magnetic fields observed anywhere in the universe. These stellar remnants arise from supernova explosions involving stars typically 10 to 25 times the mass of our sun. When such a star exhausts its nuclear fuel, the collapse of its core leads to the formation of a neutron star. However, in certain conditions, especially when the star's core has a specific rotation rate and magnetic alignment, a magnetar is born. The rapid spin and extreme compression of the magnetic field during the collapse amplify the magnetic field by up to 1,000,000,000 times that of Earth's. This causes the magnetic field lines of the star to twist and tighten as the core shrinks dramatically, concentrating an immense amount of energy into an incredibly small space. Inside the magnetar, the core's extreme density and pressure force the neutrons to align their magnetic moments in such a way that they reinforce one another. In less dense conditions, these magnetic moments would cancel out, but in a magnetar, this collective alignment magnifies the overall magnetic field. The result is a neutron star with an extraordinarily powerful magnetic field, leading to what are known as magnetar starquakes. These violent events release an outpouring of energy in the form of X-rays and gamma rays. These bursts are so intense that they can disrupt satellites orbiting Earth and even affect our atmosphere, despite being millions of light years away. Magnetars are among the most extraordinary objects in the universe, standing as enigmatic remnants of stars that once shone brightly and now leave behind an electrifying legacy of cosmic energy. Fast radio bursts, FRBs, add yet another layer of mystery to the universe's phenomena. These brief yet intense flashes of radio waves lasting only milliseconds release an energy equivalent to what our sun produces over several days. Discovered in 2007, these flashes have baffled astronomers, with their origins remaining unclear. One of the leading hypotheses is that FRBs are caused by magnetars. As we know, magnetars possess incredibly powerful and unstable magnetic fields, and sudden shifts in these magnetic fields could produce the rapid bursts of energy observed as FRBs. Some FRBs have been traced back to regions where massive stars end their lives, lending credence to this theory. However, another intriguing possibility is that FRBs are the result of catastrophic events such as the collision or merger of dense stellar remnants, like neutron stars or black holes. When these objects collide, they generate shock waves that could emit powerful radio bursts. The rare and unpredictable nature of these collisions aligns with the sporadic occurrences of FRBs, making this a plausible explanation. Interestingly, some FRBs repeat, suggesting that their source might be an object emitting energy continuously, such as a rotating neutron star in a binary system or interactions between a magnetar and its environment. Despite the enigmatic nature of FRBs, each discovery brings astronomers one step closer to understanding these powerful bursts. Their repeated occurrence and the unique circumstances under which they manifest provide vital clues to the ongoing mystery of their origins. With each new breakthrough, the cosmic puzzle of FRBs becomes a little clearer, offering us a glimpse into the universe's most extreme and fascinating phenomena. As we continue to advance our detection abilities and accumulate more data, we are inching closer to unlocking the mysteries behind some of the most extraordinary cosmic phenomena in the universe. Among these phenomena, binary star systems stand out as fascinating and complex entities. A binary star system consists of two stars orbiting a shared center of mass, and their evolution and interaction are often radically different from that of solitary stars. The dynamics within these systems create a unique blend of behaviors and events that captivate astronomers and deepen our understanding of stellar evolution. Initially, when both stars in a binary system are relatively young and still on the main sequence of their life cycle, their interaction is driven primarily by gravitational forces. Each star orbits the system's center of mass, a point that depends on the masses of the stars. In some cases, the two stars are so close that gravitational interactions become quite intricate, causing changes in their orbits. These gravitational tugs can even lead to mass transfer, where one star begins to pull material from its companion. Over time, as these stars age and deplete their nuclear fuel, they evolve away from the main sequence in a way that is more complex than single stars. The more massive star typically evolves faster, swelling into a red giant and expanding its outer layers. If the red giant's outer layers reach beyond its Roche lobe, an imaginary boundary around each star where material is gravitationally bound to it, some of this material may be transferred to the companion star. This mass transfer profoundly alters the evolution of both stars. The receiving star might experience a speed up in its rotation, accelerating its stellar life cycle. The donor star, meanwhile, could lose so much mass that it eventually becomes a white dwarf. In some scenarios, this process sets off dramatic events. If the accreting star receives enough mass, it could trigger increased nuclear activity or even explode as a supernova. This happens when the star crosses a critical mass threshold. In other instances, if the two stars in the system are close enough, they might eventually merge, leading to even more extreme events, potentially creating a single massive star or even a neutron star. Binary interactions can also give rise to exotic objects such as X-ray binaries and millisecond pulsars. In an X-ray binary, a compact remnant from one star, like a neutron star or black hole, accretes matter from a companion star, emitting intense X-rays in the process. Millisecond pulsars, on the other hand, are neutron stars that spin at incredibly high rates, hundreds of times per second, due to the material they accrete from a companion. The interplay between stars in binary systems is an intricate dance of forces and materials, producing some of the most energetic and exotic phenomena in the universe. These systems continuously challenge our understanding of stellar evolution and cosmic interactions, revealing the immense complexity of nature. In addition to binary star systems, another fascinating and hypothetical object lies at the edges of our understanding: quark stars. Quark stars are theorized to represent a state of matter that exists under conditions more extreme than those that form neutron stars. These celestial objects would form if the core of a neutron star reached a density beyond a critical threshold, causing the neutrons within it to break down into their fundamental constituents, quarks. When a massive star runs out of nuclear fuel, it typically undergoes a supernova explosion, often leaving behind a dense core. If the mass of this core is sufficient, it will collapse into a neutron star. However, if the mass and pressure surpass a certain limit, the neutrons in the core could decompose into quarks, creating a quark star. Quark stars would be composed of quark matter, a substance theorized to be even denser than neutronium, the matter that makes up neutron stars. This ultra-dense matter would likely consist of up and down quarks, particles that also make up neutrons, and possibly strange quarks, giving rise to what is sometimes referred to as strange matter. The density of quark stars would be so extreme that any additional matter falling onto them would immediately integrate into the existing quark matter, contributing very little to the increase in the star's size. However, identifying quark stars is incredibly challenging. Quark stars and neutron stars would likely exhibit very similar observable characteristics, such as similar mass and size relationships. Yet quark stars could present slight deviations from the mass-radius relationships of neutron stars, offering a potential clue for astronomers. They may also display distinct cooling patterns or emit unique bursts of energy that could be detectable by astronomical instruments. The concept of quark stars remains speculative, but it pushes the limits of our current understanding of both particle physics and stellar evolution. Confirming the existence of quark stars would not only offer groundbreaking insights into the behavior of matter under extreme conditions, but also deepen our comprehension of the fundamental forces that shape the universe. Dark matter, a mysterious and elusive component of the universe, continues to captivate scientists and laypeople alike. The evidence for its existence is drawn from multiple astronomical observations, which reveal significant discrepancies between what we expect based on traditional physics and the behaviors we actually observe in the cosmos. One of the earliest and most compelling pieces of evidence emerged from the study of galaxy rotation curves. In the 1970s, astronomers, including the groundbreaking work of Vera Rubin, observed that stars on the outer edges of galaxies rotated at the same speed as those near the center. According to Newtonian mechanics, stars further from the center should rotate more slowly, unless some unseen mass is influencing their motion. This discrepancy hinted at the presence of a hidden form of mass, an invisible substance now known as dark matter. Another pivotal clue comes from the phenomenon of gravitational lensing. Here, light from distant galaxies is bent around massive objects, like galaxy clusters, in a way that cannot be explained solely by visible matter. The extent of this bending suggests that there is far more mass in these clusters than we can directly observe, exerting the gravitational pull necessary to curve the light in such a way. This phenomenon serves as a strong indicator of dark matter's presence, as the behavior of light can only be explained by the gravitational influence of an unseen mass. Cosmic microwave background radiation, the faint afterglow of the Big Bang, also provides key insights into the universe's structure. Satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft have measured tiny temperature fluctuations in this ancient radiation. By analyzing these fluctuations and the distribution of galaxies throughout the universe, cosmologists can estimate the total amount of matter and energy present. The results reveal that only about 1/6 of this matter is the regular, visible matter we interact with daily. The remaining 5/6 is dark matter, a form of mass that, while invisible and non-interactive with electromagnetic forces, plays a crucial role in the structure and evolution of the cosmos. Perhaps one of the most striking pieces of evidence comes from the study of galaxy cluster movements. A prime example is the Bullet cluster, where two galaxy clusters collided. This collision revealed a remarkable phenomenon. The dark matter, which was detected through its gravitational influence, passed through largely unimpeded, while the normal matter, made up primarily of gas, slowed down and collided. This separation of normal matter from dark matter provided a clear visual distinction between the two, offering a direct observation of dark matter's distinct properties. Despite its invisibility and its failure to interact with light or other forms of electromagnetic radiation, dark matter's gravitational influence is fundamental to the formation and ongoing evolution of the universe. It plays a critical role in the structure of galaxies and clusters of galaxies, influencing their motion and behavior. As we continue to delve into the nature of dark matter, scientists are developing cutting-edge experiments to detect dark matter particles directly, both on Earth and in space. This remains one of the most exciting and unresolved frontiers in modern astrophysics. Alongside dark matter, another perplexing and pervasive force is dark energy, which is thought to account for the accelerated expansion of the universe. Discovered in the late 1990s through observations of distant type Sau-A supernova, dark energy is believed to comprise approximately 2/3 of the total energy density of the cosmos. Its exact nature remains one of the greatest mysteries in cosmology. One way to conceptualize dark energy is through Einstein's equations of general relativity, where it is often associated with the cosmological constant, symbolized by the Greek letter lambda. This constant represents the energy inherent in empty space, exerting a repulsive force that counteracts the gravitational pull of matter. As the universe expands, more space is created, and with it, more dark energy, amplifying the repulsive force and leading to an accelerating expansion of the universe. Alternatively, dark energy might be understood as a dynamic field distinct from gravity, known as quintessence. Unlike the static energy of the cosmological constant, quintessence evolves over time, potentially changing the rate at which the universe expands. This perspective opens the door to more flexible and complex models that could explain variations in the acceleration rate of the universe, offering a deeper understanding of dark energy's behavior. Though dark energy's effects are negligible on smaller scales, such as within individual galaxies or galaxy clusters, it exerts a profound influence on the large-scale structure of the universe. The accelerated expansion of the universe has been confirmed through various observational methods, including studies of the cosmic microwave background radiation and large-scale galaxy surveys. These observations show that galaxies are moving away from each other at an increasing rate, reinforcing the idea that dark energy is responsible for the accelerating expansion. Current and future missions, such as the Euclid satellite and the Vera C. Rubin Observatory, are set to map the distribution of galaxies across the universe with unprecedented precision. These projects aim to further refine our understanding of dark energy by examining the large-scale structure of the cosmos and monitoring how its influence has evolved over time. With these cutting-edge technologies, the study of dark matter and dark energy is poised to answer some of the most fundamental questions about the nature of the universe itself. Scientists are deeply intrigued by the potential of primordial black holes to explain the mysterious nature of dark matter. This concept has captivated astrophysicists who are eager to uncover new insights that could fundamentally reshape our understanding of both physics and the universe itself. One of the most intriguing possibilities is that dark matter might actually be composed of primordial black holes, hypothetical objects that could have formed in the very earliest moments of the universe. These objects would have emerged from intense fluctuations in density shortly after the Big Bang, marking a stark contrast to typical black holes, which form from the collapse of massive stars. Unlike the black holes we commonly observe today, primordial black holes could be much smaller, existing on a different scale entirely. This hypothesis presents a fascinating alternative origin for dark matter, something that might entirely change the way we think about the universe's unseen mass. One compelling reason to believe in this theory is the striking similarity between primordial black holes and dark matter itself. Like dark matter, primordial black holes are massive, do not emit light, and exert a gravitational influence on galaxies and galaxy clusters. These shared traits make them strong candidates for explaining the cosmic phenomena we observe, but cannot directly see. However, several major hurdles prevent this hypothesis from being fully accepted. One key challenge comes from the study of gravitational lensing, a phenomenon where light from distant stars and stars, and galaxies bends around massive objects. If primordial black holes existed in the quantities required to account for all dark matter, we would expect to observe far more instances of gravitational lensing. But current observations have failed to detect the level of lensing we would anticipate. This discrepancy places a major limitation on how numerous primordial black holes could be, making it difficult to reconcile this hypothesis with the dark matter we know must exist. In addition, primordial black holes in intermediate mass ranges might give off detectable levels of Hawking radiation, a theoretical form of radiation that black holes emit as a result of quantum effects near their event horizon. If primordial black holes were abundant, we would likely have observed this radiation or some other observable effects, such as interactions with stars and gas clouds. But thus far, no such interactions have been detected. Moreover, constraints from the cosmic microwave background radiation, the oldest light in the universe, suggest that primordial black holes can only contribute a small fraction to the overall dark matter content. Despite these challenges, the idea of primordial black holes has not been entirely dismissed. In fact, recent breakthroughs in astrophysics, particularly in the field of gravitational wave astronomy, have reignited interest in this possibility. Collaborations like LIGO and Virgo have detected mergers of black holes, some of which possess masses and frequencies that might fit the profile of primordial black holes. This intriguing development suggests that we might be closer to unraveling the true nature of dark matter, as these black hole mergers could provide clues about their primordial origins. Scientists are now focusing their efforts on exploring various mass ranges and properties of primordial black holes with a more comprehensive approach. Although dark matter particles remain elusive and alternative explanations continue to emerge, the possibility of primordial black holes remains a compelling avenue of research. Another leading candidate in the search for dark matter is weakly interacting massive particles, or WIMPs. These hypothetical particles are believed to have substantial mass, but interact primarily through the weak nuclear force and gravity. This makes them incredibly difficult to detect directly. WIMPs have emerged as a natural extension of the standard model of particle physics, particularly through theories like supersymmetry, which predicts the existence of heavier counterparts to known particles. One of these counterparts might just be a WIMP, possessing the exact properties needed to account for dark matter. The case for WIMPs as dark matter candidates is bolstered by what's known as the WIMP miracle. When scientists model the behavior of WIMPs in the early universe, they find that their mass and weak interactions would naturally have led to an abundance of dark matter particles that closely matches what we observe today. This alignment of theory and observation makes WIMPs a strong contender in the search for dark matter. However, detecting WIMPs is no small feat. It requires innovative experimental approaches, including direct detection methods, where underground detectors filled with supercooled noble gases like xenon or argon are used to spot rare interactions between WIMPs and atomic nuclei. These interactions release tiny signals of light or heat, which scientists then analyze to confirm whether they match the expected signatures of WIMP interactions. In addition to direct detection, scientists also employ indirect detection methods. These methods focus on detecting the byproducts of WIMP annihilations or decays. If WIMPs collide with one another, they could annihilate, producing gamma rays, neutrinos, or other particles detectable by instruments like the Fermi Gamma Ray Space Telescope. These efforts are essential in narrowing down the properties of dark matter and testing the WIMP hypothesis. As scientists continue their quest to understand dark matter, every discovery brings us one step closer to answering one of the universe's most profound mysteries. Particle accelerators, such as the Large Hadron Collider, have become pivotal in the ongoing quest to uncover the nature of dark matter, particularly through the creation of WIMPs, weakly interacting massive particles. These high-tech accelerators smash protons together at incredibly high energies, replicating conditions close to the moments following the Big Bang. By studying the debris produced in these collisions, scientists aim to spot the subtle signatures of missing energy or momentum, which could indicate the presence of WIMPs. Although these elusive particles have yet to be detected, the advancements in research and technology offer hope that we may eventually confirm their existence. The detection of WIMPs would solve one of the greatest mysteries in physics, the true identity of dark matter. Beyond resolving this enigma, the discovery would likely open the door to new fundamental discoveries in particle physics, altering our understanding of the universe's very fabric. As part of this ongoing search, scientists have employed an array of sophisticated techniques to detect dark matter particles, ranging from underground detectors to advanced astronomical observatories. Despite dark matter being invisible to traditional telescopes due to its lack of interaction with light, it is theorized to interact via gravity and possibly the weak nuclear force. This forms the basis for direct detection attempts. A primary method involves large underground detectors placed deep beneath the Earth's surface. These detectors are specifically designed to shield them from cosmic rays and other forms of background radiation, which could obscure potential signals. Noble gases, such as xenon or argon, are typically used in these detectors, kept in liquid form at ultra-low temperatures to increase their sensitivity. When a dark matter particle interacts with the atomic nucleus of a detector's material, it produces tiny flashes of light or minute amounts of heat. These rare interactions, despite being extraordinarily infrequent, can be detected by ultra-sensitive photodetectors and thermal sensors. Notable experiments such as Xenon 1T in Italy and Lux Zeppelin in the United States utilize large tanks of liquid xenon to monitor for such interactions. Another approach to detecting dark matter is through indirect methods, which focus on the byproducts of potential dark matter interactions in space. For instance, if dark matter particles were to annihilate or decay, they might produce gamma rays, neutrinos, or electron-positron pairs. Instruments like the Fermi Gamma Ray Space Telescope focus on regions of space, such as the centers of galaxies, where the density of dark matter is thought to be especially high. By searching for unexpected excesses of these particles, scientists hope to uncover a signature of dark matter. Particle accelerators continue to play an important role in the pursuit of dark matter. High-energy experiments, like those conducted at the Large Hadron Collider in Switzerland, provide a means of producing dark matter particles. These are inferred from the missing energy and momentum in collision events, hinting at particles that don't interact in the same way as those in the standard model. Such indirect signatures suggest the creation of new particles potentially related to dark matter, and could offer new insights into the workings of the universe. While direct evidence of dark matter is still elusive, the integration of these cutting-edge techniques and technologies is slowly narrowing down the possibilities, inching closer to solving this cosmic mystery. One of the most exciting prospects in the search for dark matter is the role of ultra-high energy cosmic rays, which are particles, primarily protons or heavier atomic nuclei that travel through space at nearly the speed of light. These particles possess energy far beyond what is achievable in man-made particle accelerators, making them some of the most energetic objects known to humanity. The precise origins of these ultra-high energy cosmic rays remain one of the most fascinating, unsolved questions in astrophysics. A potential source lies in active galactic nuclei, AGNs, which are the supermassive black holes at the centers of distant galaxies. These AGNs are surrounded by enormous accretion disks of gas and dust, which, as they spiral into the black hole, are accelerated to near light speeds. The intense jets generated by these objects could propel particles to extraordinary energies. Another possible source for these cosmic rays is gamma ray bursts, some of the most energetic phenomena in the universe. These bursts occur when massive stars collapse into black holes, or when binary neutron stars collide, releasing enormous amounts of energy in the form of explosive radiation, that could accelerate particles to ultra-high energies. Additionally, remnants of supernova explosions within our own galaxy also offer a plausible explanation. The shockwaves produced by these catastrophic events are capable of accelerating particles to incredibly high energies through a process known as Fermi acceleration, further contributing to the cosmic ray puzzle. While we have yet to identify all the sources of ultra-high energy cosmic rays, the search continues, driven by the quest to understand the universe's most energetic and mysterious particles. The investigation of these particles and their origins holds the potential to revolutionize our understanding of the cosmos. Ultimately, particle accelerators and other cutting-edge methods provide us with a glimpse into the depths of the universe, offering clues to unlock the greatest mysteries of dark matter and the forces that govern everything around us. In the vast, mysterious expanse of the universe, supernovae have long been recognized as powerful sources of lower-energy cosmic rays. Yet there exists the possibility that under the right conditions, these cataclysmic events could also serve as the birthplace of ultra-high-energy cosmic rays. These rare and extraordinarily energetic particles might be propelled by the intense magnetic fields that permeate our galaxy, possibly reaching speeds close to that of light. Interactions between cosmic rays and the interstellar or intergalactic magnetic fields may play a pivotal role in accelerating these particles. The magnetic fields, twisting and bending like cosmic rivers, amplify the energies of these particles, sending them speeding across vast expanses through a process known as diffusive shock acceleration. This process, much like the rippling waves in a storm, can propel cosmic particles to unimaginable velocities. To detect and study these elusive ultra-high energy cosmic rays, astronomers rely on ground-based observatories like the Pierre Auger Observatory in Argentina and the Telescope Array Project in Utah. These massive installations consist of vast arrays of detectors scattered over large areas to capture the secondary particle showers produced when cosmic rays collide with Earth's atmosphere. As these cosmic rays plummet through space at nearly the speed of light, they crash into molecules in Earth's atmosphere, causing an explosive chain reaction of secondary particles. By analyzing the patterns, isotopes, and energy spectra of these particles, scientists aim to unravel the mysteries surrounding the origins and acceleration mechanisms of these ultra-high energy particles. As our understanding of these cosmic showers deepens, we begin to glimpse the violent and enigmatic processes that drive some of the most energetic phenomena in the universe. Cosmic ray air showers occur when high-energy particles, primarily protons or heavier nuclei, enter Earth's atmosphere. Upon striking atmospheric particles, these cosmic rays initiate a cascade of secondary particles, producing an extensive shower that spreads across the sky. This collision begins a complex and high-energy chain reaction that generates a multitude of secondary particles. These first-generation particles, such as pions, kaons, and other hadrons, are the byproducts of the initial cosmic ray's impact. As the primary particles break apart, they create hundreds, even thousands of secondary particles, each one carrying its own energy and momentum. As these secondary particles travel deeper into the atmosphere, they collide with more molecules, creating even more particles in a process that expands exponentially. This cascading effect leads to a complex network of interactions, with each collision producing a fresh wave of energetic particles. Pions and kaons quickly decay into lighter particles such as muons, electrons, neutrinos, and photons. Photons, in particular, can undergo a process called pair production, where a photon transforms into an electron and its antimatter counterpart, the positron. Electrons and positrons can also emit photons through a process called Bremsstrahlung, feeding back into the cascade and creating even more particles. This chain reaction generates a shower of secondary particles that continues to grow wider as it propagates through the atmosphere. At lower altitudes, the composition of the shower changes. The particles within it primarily consist of photons, electrons, and muons, as many of the hadrons have decayed or lost their energy through interactions. Muons, being relatively stable and less interactive, are able to travel deep into the atmosphere and sometimes even reach the ground. Once they do, sensitive instruments like water Cherenkov tanks can detect their presence. These tanks detect Cherenkov radiation, the distinctive blue glow emitted when muons and electrons travel faster than the speed of light in water. Scintillators, another type of detector, measure the light produced when charged particles pass through specific materials. By analyzing the patterns, timing, and intensity of the detected particles, scientists can reconstruct key properties of the original cosmic ray, including its energy, arrival direction, and possibly its source. This information helps to unlock the secrets of the universe, offering insight into the origins of cosmic rays and the fundamental forces governing high-energy particle interactions. One of the most astonishing discoveries in the study of ultra-high-energy cosmic rays came in the form of the Oh My God particle, detected on October 15, 1991, by the Fly Eye cosmic ray detector in Utah. This particle possessed an energy level that was previously unimaginable, roughly 300 million electron volts, far surpassing the energy of any particle ever observed before. To put this into perspective, the kinetic energy of this single proton was equivalent to that of a baseball traveling at 90 kilometers per hour, a remarkable feat given that particle accelerators on Earth typically produce energies millions of times smaller. The detection of this particle was groundbreaking, challenging our understanding of how such extreme energies could be achieved in nature. The discovery of the Oh My God particle sparked an avalanche of questions about the potential sources of such high-energy cosmic rays. Conventional astrophysical objects, such as supernova remnants or active galactic nuclei, could not account for the staggering energies observed. Some scientists speculated that more exotic and rare cosmic events, such as the collision of neutron stars, the jets emitted by supermassive black holes, or even processes that occurred during the early universe just after the Big Bang, might be responsible for these extraordinary particles. The quest to understand the origins and mechanics of these ultra-high-energy cosmic rays continues to push the boundaries of our knowledge, promising new revelations about the forces and events shaping the cosmos. In the vast expanse of the universe, cosmic phenomena often defy our understanding, especially when it comes to the high-energy particles known as cosmic rays. Among the most fascinating discoveries in the field of astroparticle physics is the Oh My God particle, a cosmic ray with an energy far surpassing anything previously observed. This astonishing particle presented an intriguing puzzle related to the Ghon-Zippen-Kussmann limit, a theoretical upper bound on the energy of cosmic rays. According to this limit, cosmic rays with energies above approximately 5 million electron volts should interact with the cosmic microwave background radiation, losing energy over vast distances. This would typically prevent them from traveling through space unscathed. However, the detection of the Oh My God particle and other ultra-high energy cosmic rays has suggested otherwise. Observations indicate that these particles either originate from relatively nearby extragalactic sources or that an unknown mechanism allows them to preserve their energy over unprecedented distances. The discovery of this particle remains a pivotal moment in our understanding of cosmic rays, sparking continued research and debate over the processes that might produce such extreme energies. As the study of cosmic rays progresses, scientists are delving deeper into the challenges these particles present. Not only do they offer valuable insights into the most energetic phenomena in the universe, but they also pose significant risks for human space exploration. Cosmic rays originating from the sun, distant stars, and other cosmic sources can have profound effects on both spacecraft and astronauts. Unlike Earth's surface, where the magnetic field and atmosphere offer protection, space lacks these natural shields, leaving astronauts directly exposed to high-energy particles. These particles can penetrate human tissue and spacecraft materials, leading to a range of potential health issues. The biological effects of prolonged exposure to cosmic rays are a primary concern for space agencies. High-energy radiation can damage DNA and cellular structures, increasing the risk of cancer, cataracts, neurological disorders, and other severe health complications. The longer the space mission, such as a journey to Mars, the greater the cumulative exposure and the associated risks. This has driven the need for advanced protective measures in space travel, especially as humanity pushes further into the cosmos. Furthermore, cosmic rays also pose a threat to the electronics on spacecraft through a phenomenon called single event effects. When high-energy particles strike electronic components, they can induce errors, disrupt operations, or even permanently damage critical systems. Ensuring the reliability of spacecraft and their instruments under these conditions is a key challenge for mission planning and engineering. To mitigate these risks, several strategies are employed in spacecraft design. Shielding materials, such as polyethylene and water, help reduce exposure to cosmic rays, although complete protection is not feasible due to the impracticality of carrying excessively heavy shielding. Additionally, spacecraft trajectories and mission durations are carefully planned to minimize exposure during periods of heightened solar activity, such as solar flares, which can elevate radiation levels even further. In parallel, space agencies are exploring medical countermeasures and pharmaceuticals that might help protect astronauts from radiation-related health issues. Continuous monitoring of radiation levels using onboard sensors is another critical component of mission safety. Real-time data allows mission control teams to assess and respond to elevated risks, ensuring astronaut safety throughout the duration of the mission. The challenge of cosmic rays in space exploration is far from trivial. However, through a combination of advanced engineering, mission planning, and ongoing research into protective measures, the goal is clear: to safeguard astronauts as humanity continues to venture into the unknown. By expanding our understanding of cosmic rays and finding ways to mitigate their impact, we pave the way for the future of long-duration space travel. At the forefront of this research are neutrino detectors, instruments that allow scientists to peer into the heart of some of the universe's most dramatic events. Neutrinos, unlike photons or charged particles, rarely interact with matter. This property makes them incredibly difficult to detect, yet also renders them perfect messengers from the extreme environments in which they originate. These elusive particles can travel directly from the core of a supernova or the depths of the sun, carrying crucial information without being deflected or absorbed by intervening matter. Neutrino detectors have opened a window into processes like nuclear fusion inside stars. The sun, powered by fusion reactions, emits a constant stream of neutrinos, and studying these particles gives scientists direct evidence of the sun's inner workings. This research validates models of stellar physics and offers insights into the fundamental processes that drive the cosmos. Similarly, the detection of neutrinos from supernovae allows scientists to study the explosive deaths of massive stars. These events are responsible for the production of heavy elements in the universe and the birth of neutron stars and black holes. Neutrinos thus provide a direct link to the most violent and energetic events in the cosmos, offering a glimpse into the inner workings of stellar evolution. But neutrinos also play a crucial role in the broader understanding of particle physics. The phenomenon of neutrino oscillation, where neutrinos change from one type to another, has provided compelling evidence that they possess mass, challenging earlier assumptions. This discovery has profound implications for our understanding of the fundamental forces that govern the universe. Moreover, neutrinos from extragalactic sources open up new avenues of research in high-energy astrophysics. These particles may originate from active galactic nuclei or other mysterious cosmic phenomena, offering researchers invaluable clues about the most energetic processes in the universe. By studying neutrinos, scientists gain access to a perspective that would otherwise remain hidden, an opportunity to explore the furthest and most enigmatic corners of the cosmos. As the study of neutrinos continues to evolve, it holds the promise of revealing more about the universe's most extreme events, from the birth of stars to the formation of black holes. In doing so, these particles offer a unique and powerful tool for unlocking the mysteries of the universe. Through continued exploration and discovery, we can better understand the fundamental forces at play in the cosmos and deepen our knowledge of the universe itself. Time dilation, one of the most intriguing phenomena in Einstein's theories of relativity, serves as a perfect example of how theoretical physics connects with the everyday technologies we rely on. It's a concept that goes beyond abstract equations and transforms into a practical, essential element for our modern world. Time dilation isn't just a curiosity of the universe. It plays a critical role in the functioning of the Global Positioning System, GPS, a technology many take for granted but depend on daily. GPS satellites orbit the Earth at high velocities and at varying altitudes, and as a result, they experience time differently than clocks on the Earth's surface. According to general relativity, time moves slower in stronger gravitational fields. This means that clocks on the Earth's surface tick slightly slower than those located further away in space, where gravitational pull is weaker. But there's more. Special relativity, which addresses the effects of high speeds on time, tells us that time on the satellites also runs slower compared to an observer at rest on Earth. Without compensating for these time differences, GPS would not work accurately. A discrepancy of even a tiny fraction of a second can lead to significant errors in positioning. The combined effects of special and general relativity mean that clocks on GPS satellites actually tick faster than those on Earth, by about 38 microseconds per day. Though this may seem like an almost imperceptible difference, over time it would lead to disastrous errors in position calculations. In fact, the error could grow as large as 10 kilometers per day. To counter this, the engineers behind GPS technology preset the satellite clocks to tick slightly slower before they are launched. This way, by the time they reach orbit, their clocks will be synchronized with those on the Earth's surface. Moreover, onboard computers constantly adjust the satellite time to account for motion and gravitational differences, ensuring that the system remains precise. This complex interplay between special and general relativity isn't just a theoretical marvel, it is essential for the functioning of everyday services. From navigation and mapping to telecommunications and even financial transactions, the accuracy of GPS is critical. Time dilation adjustments highlight the importance of Einstein's groundbreaking work, showing how abstract physics principles have direct and profound effects on our lives. It's a reminder that our understanding of the cosmos impacts everything, from how we navigate the Earth to how we communicate and exchange information. Another fascinating aspect of Einstein's theory of general relativity is the prediction of gravitational waves, ripples in the fabric of space-time itself, created by some of the most violent events in the universe. These waves travel at the speed of light, and they are generated when massive objects undergo extreme accelerations, such as the merging of black holes or neutron stars, supernova explosions, or the rapid rotation of massive stars. Gravitational waves carry with them vital information about the processes happening in far-off regions of space, offering scientists a new way to observe and study the cosmos. However, detecting these waves is no easy task. Gravitational waves cause space-time to stretch and compress by minuscule amounts, smaller than the diameter of a proton. To measure such subtle distortions, highly sensitive instruments are required. The Laser Interferometer Gravitational Wave Observatory, LIGO, is one such tool, with two L-shaped interferometers located in Washington State and Louisiana. Each arm of these interferometers is kilometers long, and a laser beam is split and sent down both arms. If a gravitational wave passes through, it causes a tiny change in the length of the arms, altering the time it takes for the laser beams to return and recombine. By measuring the interference pattern created when the beams return, LIGO can detect even the smallest variations in space-time. In 2015, LIGO made history by directly detecting gravitational waves for the first time, specifically from the collision of two black holes. This groundbreaking discovery not only confirmed a major prediction of general relativity, but also opened the door to a new way of observing the universe. With the advent of additional detectors, such as Virgo in Italy and Kagra in Japan, the ability to pinpoint the sources of gravitational waves is improving. By studying these cosmic ripples, scientists hope to uncover hidden details about the universe's most mysterious and powerful events. Wormholes, hypothetical passages through space-time, have long fascinated both physicists and the general public. The idea of a shortcut between distant parts of the universe is tantalizing, especially when considering the possibility of faster-than-light travel. According to solutions to Einstein's equations, wormholes could theoretically exist as tunnels in space-time, with two ends located in different parts of the universe. If such a passage were stable and traversable, it could allow for instantaneous travel between far-off locations, bypassing the restrictions of light-speed travel. But the notion of using wormholes as practical shortcuts faces several enormous challenges. The most pressing issue is their stability. Most solutions to the wormhole equations predict that the wormhole would collapse almost immediately upon forming, preventing anything, including light, from passing through. To keep a wormhole open and stable, scientists hypothesize that exotic matter with negative energy density would be required. This matter would counteract the natural tendency of the wormhole to pinch off. However, the creation or manipulation of such exotic matter remains far beyond our current technological and scientific capabilities. Even if a stable wormhole could be created, the intense gravitational forces near the wormhole's throat could pose another serious challenge. These forces could stretch and compress anything trying to pass through, a process known as spaghettification. This would make any attempt at traversing a wormhole potentially dangerous, as it could destroy the object or person attempting the journey. While wormholes remain purely theoretical and speculative, their connection to general relativity and space-time continues to captivate the imagination of scientists and science fiction enthusiasts alike. The search for answers to these profound questions about the nature of space and time is ongoing, and even if wormholes remain a distant dream, the exploration of such concepts pushes the boundaries of our understanding of the universe. Furthermore, solutions involving wormholes sometimes simply the existence of causality paradoxes, like the possibility of time travel, which introduces a host of the theoretical and practical complications, while wormholes remain a fascinating idea in theoretical physics and a staple of science fiction. Actual evidence for their existence or our ability to use them for travel remains elusive. As of now, they are rich arenas for thought experiments and underline the profound complexities of space-time, but they are far from providing a practical solution for fast-after-than-light travel. Nonetheless, studying wormholes continues to push the boundaries of our understanding, challenging scientists to think beyond the limits of known physics. Frame dragging, also known as the lens-throwing effect, is a fascinating phenomenon that occurs in the vicinity of rotating massive objects. According to Einstein's theory of general relativity, mass and energy can warp space-time, creating the gravitational effects we observe. However, when an object rotates, it does more than just warp space-time, it also drags it along with it. Rotation. Imagine space-time as a kind of viscous fluid and a rotating object like a star or black hole. As a star, as the object spins it, twists the space-time around it. This effect is most pronounced near extremely massive and rapidly rotating bodies such as neutron stars and black holes. The closer one gets to these objects, the stronger the frame dragging effect becomes. Detecting frame dragging is incredibly challenging because its effects are subtle and require sensitive instrumentation. One of the most compelling confirmations of this phenomenon, CAM. From NASA's Gravity Probe B mission launched in 2004, the spacecraft carried ultra-precise gyroscopes intended to measure the tiny angle changes caused by the Earth's rotation dragging space-time around it. After years of data analysis, the results confirmed the presence of frame dragging, albeit at a very small scale. Frame dragging has significant implications for our understanding of the cosmos around rotating black holes. For instance, this effect could influence the paths of particles and light, shaping the structure and dynamics of Raytheon disks and jets emitted by the enigmatic objects. By studying frame dragging, scientists not only test and refine our understanding of general relativity, but also gather crucial insights into the complex behaviors near some of the most extreme environments in the universe. The twin paradox is a thought experiment that offers a vivid demonstration of time dilation, a concept rooted in Einstein's theory of special relativity. In this scenario, imagine two identical twin sun remains on Earth, while the other embarks on a journey through space, a TAVE. Velocity closer to the speed of light. According to special relativity, the twin traveling at high speed experiences time more slowly compared to the twin who stays behind. Here's how the paradox unfolds. The traveling twin sets off on a journey to a distant star at near light speed, and then returns to Earth upon reuniting with the Earthbound twin. The traveling twin finds less time has passed for them than for their sibling who remained on Earth. While the Earthbound twin may have aged, say, 10 years, the traveling twin might have aged only a fraction of that time, depending on the exact speed and duration of the journey. This discrepancy arises because, as per special relativity, moving clocks runs lower when observed from a stationary frame of reference. The term paradox emerges because it initially seems counterintuitive. One might wonder if each twin could consider the other as moving. So, why wouldn't they both experience time dilation equally? Their solution lies in the fact that the traveling twin undergoes acceleration and deceleration during their journey, breaking the symmetry of the situation. This makes the traveling twin's frame of reference non-inertial, different from the stay-at-home twin's inertial frame. The Whitwin paradox illustrates the real and measurable effects of relativity. Indeed, this effect is not just a theoretical curiosity, it has practical applications, such as in the functioning of the global positioning system satellites, where time dilation must be accounted for to maintain the accuracy of navigation signals. Thus, the twin paradox offers a compelling glimpse into the strange and counterintuitive nature of time in our relativistic universe. Urseth, a mysterious gamma-ray glow at the center of our galaxy, often referred to as the galactic center Jevek, has puzzled astronomers since its discovery. These high-energy gamma rays detected by telescopes, like the fiery gamma ray, space telescopes seem to emanate from an area densely packed with stars, dust, and energetic phenomena. The exact source of this gamma-ray emission is still under investigation, and several compelling theories have been proposed. One significant hypothesis suggests that dark matter particles might be annihilating each other. Rinth, the denser region of the galactic center dark matter, which makes up a substantial portion of the universe's mass, remains largely undetectable except through its gravitational effects. If dark matter particles occasionally collide and annihilate, they could produce high-energy gamma rays as a byproduct. This would be a groundbreaking discovery, shedding light on the elusive nature of dark matter. Another theory attributes the gamma-ray excess to a population of millisecond pulses, these rapidly rotating neutron stars that emit beams of radiation including gamma rays. They are thought to be numerous in the crowded regions of our galaxy. If these millisecond pulsars are indeed the source, it would mean that our understanding of the stellar population and high-energy processes in the intergalactic core needs significant adjustment. Alternatively, the gamma-ray glow could result from interactions between cosmic rays and the dense gas clouds in the galactic center. Cosmic rays, which are high-energy particles traveling through space, can collide with gas atoms, producing gamma rays in the process. Given the complex environment of the galactic center with its intense magnetic fields and high stellar activity, such interactions could plausibly generate the observed gamma-ray excess. As scientists continue to explore these possibilities, each potential explanation offers a fascinating glimpse into the dynamic and energetic processes at play in our galaxy's core. Understanding the true source of this gamma-ray glow not only unravels a cosmic mystery, but also enhances our knowledge of the fundamental forces and particles that shape the universe. Supermassive stars like R136 or 1, found in the dense star cluster R136, in the Large Magellanic Cloud, represent some of the most extreme cosmic phenomena. Forming such enormous stars, which can have masses hundreds of times that of our sun, require specific and exceptional conditions that are still a subject of intense study and debate among astronomers. The formation process begins within giant molecular clouds, vast regions of cold gas and dust, where stars are born. For a supermassive star to form a particularly dense region within one of the ESA clouds must collapse under its own gravity. The key to generating a star as massive as R136A1 lies in the accumulation of an enormous amount of material from the surrounding cloud. This might happen in regions where star formation is particularly vigorous, and the molecular cloud has unusually high mass and density once the progenitor gas cloud collapses. It forms a protostar that rapidly accretes more and more material in environments like their 136 star cluster neighboring stars, and intense radiation can drive these accretion process, not only feeding the growing protostar, but also helping to clear away excess gas that might otherwise limit its growth. Despite these aiding factors, maintaining stability is a challenge because the massive star's intense radiation pressure can counteract gravity and hinder further growth. As these supermassive stars evolve, they burn through their nuclear fuel at an incredibly rapid rate. Their cores reach extreme temperatures and pressures, allowing for the fusion of heavier elements. However, this accelerated fusion process means that their lifespan is astonishingly brief, typically just a few million years, compared to the billions of years for lower mass stars like our sun towards the end of their life cycles. Supermassive stars undergo dramatic transformations. They might explode a supernova or even hypernova, releasing vast amounts of energy and enriching the interstellar medium with heavy elements. In some cases, they leave behind a dense core that collapses into a black hole. Through these cataclysmic ends, supermassive stars play a crucial role in the cosmic cycle of matter and the evolution of galaxies. Each stage of their life cycle offers invaluable insights into the extreme conditions and processes that shape the universe. High-velocity clouds are enigmatic, fast-moving clouds of gas that zip through the halo of the Milky Way at speed hundreds of kilometers. Second, relative to the galaxy's rotation, their origins are varied and complex, pointing to multiple potential sources and mechanisms that contribute to their formation. One leading hypothesis suggests that some of these high-velocity clouds are remnants of the galactic fountain process. In this scenario, supernova explosions within the Milky Way's disk propel gas outward into the halo. This gas then cools, condenses, and eventually falls back toward the galactic plane during its return. This recycled material can appear as high-velocity clouds, essentially rejuvenating the galaxy with newly cooled gas that contributes to future star formation. Another plausible source for high-velocity clouds is the interaction between the Milky Way and its satellite galaxies, as smaller galaxies like the Melanic clouds orbit and occasionally pass through the Milky Way's halo. Their gravitational interactions and tidal forces can strip gas from the sea satellites. This stripped gas can't then manifest as high-velocity clouds. Observations suggest that the Melanic stream, a long tail of gas trailing from the Melan I clouds, may contribute significantly to these high-velocity phenomena. High-velocity clouds are an enigmatic feature in the study of our Milky Way galaxy, with some scientists proposing that they could be primordial gas remnants from the very formation of our galaxy. These clouds might contain relatively unprocessed, pristine material, offering a glimpse into the early universe. This gas reservoir, which could be part of the Milky Way's halo, carries the legacy of cosmic conditions from long before the formation of the galaxy itself. By studying these clouds, astronomers can uncover valuable insights into the nature of the early universe and the processes that shape the galaxies we observe today. Regardless of their origins, high-velocity clouds provide critical clues to the ongoing processes that shape and define the dynamics of the Milky Way. Through careful observation and analysis, astronomers continue to unveil the complex layers of our galaxy's history. These clouds, traveling at high velocities, serve as a unique window into the constantly evolving dynamics of the Milky Way. Galaxies are never static. Instead, they are shaped by their interactions with one another, including the dramatic and awe-inspiring events that unfold during galaxy collisions and mergers. These cosmic events occur over time spans of millions to billions of years, forever altering the shape and behavior of the galaxies involved. Initially, the gravitational forces between two approaching galaxies begin to draw them closer together. Contrary to popular belief, galaxies don't typically collide in the sense of violent impacts between stars. Those stars are too far apart for that to happen. Instead, it is the immense gravitational forces that reshape the entire structure of both galaxies. As galaxies near each other, their gravitational fields stretch and twist their shapes. The once symmetrical arms of a spiral galaxy may elongate, or in some cases even spiral in unexpected ways. The gas and stars within these galaxies can be flung outward, reaching into intergalactic space, while tidal forces wreak havoc on their shapes. But these encounters don't end in destruction. In fact, one of the most profound outcomes of these interactions is the intense compression of gas within the galaxies. This leads to rapid bursts of star formation, an event known as starbursts. During starbursts, new stars form at an accelerated rate, much higher than in more peaceful times. These bursts add a burst of energy to the galaxies, and as the galaxies pass through each other, gravity pulls them back for additional encounters. The cumulative effect of these interactions is the gradual coalescence of both galaxies into one, often larger and more complex galaxy over time. The merging process results in a massive rearranging of stars and gas, smoothing out the chaotic motions of the galaxy's components. The original shapes of the galaxies evolve dramatically. For instance, the merger of two spiral galaxies often results in an elliptical galaxy marked by random stellar orbits and a spheroidal shape. This transformation is central to the hierarchical model of galaxy formation, which suggests that larger galaxies form from the merging of smaller ones. The evidence of this cosmic galactic cannibalism is visible in the strange shapes, tidal tails, and stellar streams seen in many galaxies today. These remnants of past collisions reveal a deep history of galactic growth, including that of our own Milky Way, which is still in the process of absorbing smaller satellite galaxies like the Sagittarius Dwarf Galaxy. Beyond the physical structure of galaxies, mergers also have a profound impact on the supermassive black holes that lie at their centers. When two galaxies merge, the influx of gas towards their central black holes can fuel them, often leading to an active galactic nucleus. These energetic black holes shine brightly, sometimes as quasars, and reveal the immense power of these cosmic objects. The impact of galactic mergers stretches beyond the immediate physical changes in the galaxies involved. These processes contribute significantly to the evolution and diversity of the cosmos. One of the more mysterious aspects of the Milky Way is the strange ripples seen in its disk, which continue to intrigue astronomers. These ripples, or oscillations, manifest as variations in the velocity and distribution of stars and gas within the galactic disk. They hint at past disturbances that continue to affect the structure of our galaxy. Some of these disturbances may have originated from the gravitational interactions with nearby satellite galaxies, such as the Sagittarius Dwarf Galaxy. This smaller galaxy, as it orbits the Milky Way, exerts a tidal influence, inducing waves across the galactic disk, much like ripples formed in water when a pebble is dropped. However, these galactic interactions span millions of years, and the effects can linger long after the initial encounter. Ancient galactic collisions, or interactions with clumps of dark matter, might also be responsible for these ripples. These earlier events could have stirred up the gas and stars in the Milky Way, leaving lasting marks that remain visible in the galactic disk. Even as the Milky Way settles back into a more stable state, these ripples persist, providing a record of the dynamic forces at play in our galaxy's long history. These ongoing disturbances not only reveal the past history of the Milky Way, but also offer hints about the hidden, invisible processes shaping our galaxy today. In the heart of the Milky Way, the galactic bar, a central elongated structure, plays a crucial role in shaping the galaxy's dynamics. As it rotates, the galactic bar exerts powerful gravitational forces on the rest of the galaxy, triggering waves and spiral patterns in the disk. This internal dynamical effect isn't just a passive occurrence. It actively perpetuates and amplifies ripples that ripple through the galaxy's disk, contributing to the complex and intricate structure we observe today. Recent studies using data from the Gaia Space Observatory have provided groundbreaking insights into these ripples. Gaia's unprecedented precision in measuring the positions, distances, and motions of stars across the Milky Way has allowed astronomers to map the galaxy's oscillations with remarkable accuracy. This wealth of information gives scientists an unparalleled view into the Milky Way's past interactions and internal dynamics, shedding light on the ongoing processes that shape the galaxy's evolution. Understanding these ripples not only offers a glimpse into the galaxy's past, but also provides a window into its future, revealing the subtle but powerful forces that govern its cosmic journey. Amidst these cosmic revelations, the hypothesis of Planet 9 has sparked considerable excitement within the astronomical community. A potential unseen planet lurking in the far reaches of our solar system could explain some of the most puzzling behaviors observed in distant objects in the Kuiper Belt. These objects, many of which are located far beyond Neptune, follow highly elongated and tilted orbits, challenging our understanding of the solar system's gravitational forces. Recently, astronomers have noticed something even more perplexing. These distant objects do not follow random orbital paths. Instead, their perihelia, the closest points in their orbits to the Sun, seem to cluster together. This peculiar clustering of orbits strongly suggests the gravitational influence of a massive unseen body, potentially Planet 9. With an estimated mass about 10 times that of Earth, the presence of Planet 9 could account for these unusual orbital alignments and behaviors. But that's not all. Planet 9's gravitational pull may also explain other anomalies within our solar system. Some of the extreme trans-Neptunian objects exhibit orbital inclinations that rise to high angles relative to the solar system's plane. These tilted orbits are difficult to justify without invoking an additional gravitational force. And when researchers simulate the solar system's dynamics, incorporating a hypothetical Planet 9 into their models, the resulting orbital alignments closely match the observed clustering of distant objects. This strengthens the case for the existence of a massive, distant planet shaping the outer solar system. Despite the compelling evidence, Planet 9 remains elusive. Its immense distance and slow movement make it extremely challenging to detect with current technology. But astronomers aren't giving up. Next-generation telescopes and advanced sky surveys are actively seeking this hidden planet, hoping to confirm its existence once and for all. If Planet 9 is discovered, it will revolutionize our understanding of the solar system's architecture and its formation, offering new insights into the forces that have shaped the outer reaches of our cosmic neighborhood. Moving closer to Earth, the moon's formation remains one of the most fascinating chapters in the story of our solar system. The leading theory, known as the giant impact hypothesis, proposes that the moon formed from the debris left behind after a colossal collision between the early Earth and a Mars-sized protoplanet called Theia. This catastrophic event, occurring over 4 billion years ago, would have ejected a tremendous amount of material into Earth's orbit, eventually coalescing to form the moon. This hypothesis not only explains the moon's origin, but also offers a deeper understanding of its composition. Lunar samples brought back by Apollo missions revealed that the moon consists largely of silicate material, similar to Earth's crust and mantle. Interestingly, the isotopic composition of oxygen in lunar rocks closely matches that of Earth, further supporting the theory that the moon's material primarily came from Earth's outer layers and from Theia, both of which had already undergone significant differentiation. The aftermath of this giant impact would have produced a molten disk of superheated silicate vapor and liquid around Earth. As the disk cooled, it condensed into the proto-moon. The high temperatures from the collision would have caused volatile elements to vaporize and escape, explaining why the moon is deficient in these elements compared to Earth. Moreover, the moon's core is significantly smaller relative to its size than Earth's core. Most of Theia's iron-rich core likely merged with Earth's core during the collision, while the material that formed the moon was mostly mantle and crustal material, again explaining the moon's iron-poor composition. The giant impact hypothesis not only clarifies the moon's formation and composition, but also provides insights into the violent, dynamic environment of the early solar system. By understanding this process, scientists are piecing together the narrative of planetary formation and the shared history between Earth and its natural satellite, the Moon, an enduring bond that has shaped the course of our planet's evolution. The hexagonal storm at Saturn's North Pole stands as one of the most captivating and enigmatic phenomena in our solar system. First discovered by the Voyager spacecraft in the early 1980s, this extraordinary six-sided jet stream has since been observed in greater detail by the Cassini spacecraft, unraveling even more about its awe-inspiring nature. Spanning an impressive 30,000 kilometers, the storm's geometric precision and remarkable stability have left scientists intrigued, prompting extensive research into its origins and behavior. The leading theory behind the formation of Saturn's hexagonal storm involves a combination of fluid dynamics and atmospheric phenomena. Saturn, a gas giant primarily composed of hydrogen and helium with traces of heavier elements, provides a unique setting for such a phenomenon. The hexagon is thought to arise from the differential rotation of Saturn's atmosphere, where jet streams interact in the planet's polar region. In essence, Saturn's atmosphere consists of clouds moving at different speeds and directions, creating intricate flow patterns. These flows come together to form the striking hexagonal shape we observe today. Remarkably, scientists have been able to replicate similar polygonal shapes in laboratory simulations. By rotating fluids within a cylindrical container at varying speeds, they have observed how shear forces and resonant waves can create polygonal patterns. In much the same way Saturn's atmosphere behaves, the hexagonal shape emerges from the interaction between deep atmospheric jets and velocity differences that generate standing wave patterns. Additionally, a powerful polar vortex plays a crucial role in maintaining the storm's stability. Acting as an anchor, this vortex holds the hexagonal jet stream in place, allowing it to rotate consistently. This vortex helps to preserve the storm's shape, even over long periods. Unlike Earth's weather systems, which shift relatively quickly, Saturn's atmospheric storms can endure for decades, or even centuries, due to the planet's uniformity and lack of a solid surface to disrupt atmospheric flow. This long-term stability allows scientists to study Saturn's atmosphere under extreme conditions, providing valuable insights into planetary atmospheres, fluid dynamics, and even the broader principles that govern atmospheric behavior on exoplanets. The study of Saturn's hexagonal storm is more than just an exploration of a strange celestial phenomenon. It offers an invaluable opportunity to understand fluid dynamics in cosmic environments. By comparing Saturn's storm to similar occurrences elsewhere, scientists can better grasp the mechanics of planetary atmospheres and how fluid behavior can manifest on a variety of worlds. Venus, with its retrograde rotation, presents another fascinating puzzle that continues to intrigue astronomers. Unlike Earth, Mars, and most other planets in our solar system, which rotate counterclockwise when viewed from above their north poles, Venus spins in the opposite direction, clockwise. As a result, the sun rises in the west and sets in the east on Venus, an intriguing reversal of the norm. The unusual rotational behavior of Venus has led to several competing theories that attempt to explain this anomaly. One prominent theory suggests that Venus may have experienced a colossal impact during the early stages of the solar system's formation, much like the collision that led to the creation of Earth's moon. Such a massive impact could have altered Venus's rotational angular momentum, effectively reversing its spin direction. Another theory proposes that tidal forces from the sun, combined with Venus's dense atmosphere and thick sulfuric acid clouds, could have gradually slowed the planet's rotation over billions of years. This friction would create a situation similar to how the Earth's tidal interactions with the moon have gradually slowed Earth's rotation, with minor forces reversing the spin direction over an extended period. Additionally, the interactions between Venus's thick atmosphere and its internal dynamics could also play a role in its retrograde rotation. Venus's atmosphere circulates much faster than the planet itself, a phenomenon known as atmospheric superrotation. This superrotation exerts significant surface stresses that could, over astronomical timescales, influence the planet's rotational direction. The combined effect of atmospheric friction, tidal forces, and internal dynamics offers a complex but intriguing explanation for Venus's reverse spin. Venus's slow rotation, which takes about 243 Earth days to complete one full turn on its axis, means that its atmosphere moves faster than the planet itself. This imbalance adds another layer of complexity to our understanding of planetary dynamics. By studying Venus's retrograde rotation, scientists not only uncover the history of our nearest planetary neighbor, but also enrich our knowledge of planetary formation and the intricate forces that shape the evolution of worlds. In both cases, Saturn's hexagonal storm and Venus's retrograde rotation, we see the importance of fluid dynamics in understanding planetary behavior. These phenomena help us uncover the hidden forces that shape the atmospheres of distant worlds, ultimately deepening our comprehension of the universe's cosmic machinery. In exploring the vast wonders of our solar system and beyond, comparing celestial bodies like Venus with others opens a doorway into understanding the incredible diversity of planetary processes that shape the universe. From the peculiarities of Venus's thick atmosphere to the complexities of distant stars, each celestial body provides a unique window into the cosmic mechanisms that govern our universe. Take, for example, the mysterious phenomena in Saturn's rings, specifically the enigmatic spokes that have puzzled scientists for decades. These ghostly radial bands seem to dance across Saturn's otherwise orderly rings, creating a striking contrast. But what causes these eerie spokes? The answer lies in the intricate relationship between Saturn's magnetic field and the tiny ice particles within its rings. Saturn's rings, made up of a mix of ice and rock, contain particles that range from the size of dust grains to enormous boulders. It is the electrostatic charging of these smaller ice particles that leads to the formation of spokes. When these particles interact with ultraviolet light from the sun, or energetic particles in Saturn's magnetosphere, they become electrically charged. Saturn's immense magnetic field then lifts these charged particles slightly above the ring plane and aligns them along magnetic field lines. This interaction causes the spokes to form and move across the rings, sometimes at varying speeds. Essentially, it's as if invisible magnetic forces are gently pushing these tiny particles across the sky. These spokes are most visible when Saturn's rings are aligned edge-on to the sun during the planet's equinoxes. The Cassini spacecraft, which orbited Saturn for over a decade, provided invaluable data and images that enhanced our understanding of this phenomenon. While much remains to be discovered, the interplay between sunlight, magnetic fields, and charged particles offers a fascinating glimpse into the complexity of Saturn's majestic rings. Moving from the icy rings of Saturn to the violent bursts of energy across the cosmos, let's dive into one of the most powerful and luminous explosions the universe has to offer: gamma-ray bursts, GRBs. These intense, high-energy events can release more energy in just a few seconds than the sun will over its entire 10 billion-year lifespan. GRBs come in two primary varieties: long-duration and short-duration bursts. Long-duration GRBs, which last more than 2 seconds, are typically associated with the collapse of massive stars, often resulting in the formation of black holes or neutron stars. As these newly formed cosmic objects exert immense gravitational forces, surrounding material spirals inward at incredible speeds, creating heat and pressure so extreme that gamma rays are emitted in vast quantities. On the other hand, short-duration GRBs, lasting less than 2 seconds, are thought to originate from the merger of two compact objects, such as neutron stars or a neutron star colliding with a black hole. The violent gravitational disruption caused by these collisions results in an outpouring of gamma rays, much like the long-duration bursts, but originating from an entirely different cosmic scenario. In both cases, the energy is channeled into narrow, focused jets that travel at nearly the speed of light. When one of these jets points directly toward Earth, we observe it as a gamma-ray burst, one of the most extreme and powerful events in the universe. The incredible energy behind these bursts is a result of the rapid rotation and intense magnetic fields that arise during these cosmic events, converting vast amounts of gravitational energy into radiation. The study of gamma-ray bursts has revolutionized our understanding of the universe. Space telescopes such as the Hubble Space Telescope and the Fermi Gamma Ray Space Telescope have provided critical observations that not only reveal the immense power of GRBs, but also their role in the evolution of galaxies. These bursts contribute to the creation of heavy elements and influence the formation of new stars and galaxies, acting as one of the universe's most potent forces in shaping cosmic history. Among the most fascinating events in the universe are kilonovae, spectacular explosions that occur when two neutron stars, or a neutron star and a black hole, spiral toward each other and merge. These cataclysmic events unleash unimaginable amounts of energy, creating extreme conditions that forge some of the heaviest elements in the universe, such as gold and platinum. But to understand how kilonovae form, we must first understand the nature of neutron stars, dense remnants of massive stars that have exploded in supernovae. When two neutron stars are gravitationally bound, they lose energy through gravitational waves, causing them to spiral closer until they eventually collide. During this collision, neutron-rich material is ejected into space, where it undergoes rapid neutron capture, a process known as the R process. This process is responsible for the creation of heavy elements. In addition to emitting a bright burst of gamma rays, the merger creates a glowing cloud of radioactive material that shines as it decays. This phenomenon is what we observe as a kilonova, a cosmic event that not only illuminates the universe, but also helps us understand the origins of heavy elements. Prior to the detection of kilonovae, scientists speculated that supernovae were the primary sites for the formation of these elements. However, discoveries such as the 2017 GW170817 merger have shown that neutron star mergers play a crucial role in the creation of gold, platinum, and other heavy elements. By studying the light emitted by kilonovae, scientists can detect the specific wavelengths of various elements as they form. This allows them to unravel the mysteries of where and how the universe's heaviest elements are forged. Such findings not only deepen our understanding of cosmic events, but also connect us to the very elements that make up our planet and even our own bodies. In this way, every kilonova serves as a reminder of the interconnectedness of the universe, where the smallest particles of stardust contribute to the grand tapestry of life. When neutron stars collide, the event is nothing short of spectacular, an awe-inspiring cosmic phenomenon that dramatically shifts our understanding of the universe. Neutron stars, the incredibly dense remnants of massive stars that have exploded in supernovae, are the result of some of the most extreme processes in astrophysics. In a binary system, where two neutron stars orbit each other, the immense gravitational forces at play cause them to slowly spiral toward one another. Over millions of years, these stars lose energy by emitting gravitational waves, the very fabric of space-time rippling as they draw closer. As these stars approach a critical distance, their gravitational pull becomes titanic, causing the stars to deform, stretch, and emit increasingly intense gravitational waves. These waves intensify, reaching a crescendo just before the stars merge in a cataclysmic explosion, one that releases an unimaginable amount of energy. This collision sets off a chain of extraordinary events, starting with the emission of a gamma-ray burst, a flash of gamma rays so powerful it can be detected across billions of light years. In tandem with this, the collision ejects an enormous amount of neutron-rich material into space. These rapidly expanding ejecta undergo a process known as the R process, where rapid neutron capture occurs, forging some of the heaviest elements in the universe, such as gold, platinum, and uranium. After the gamma-ray burst fades, the ejected material continues to glow as it decays, giving rise to what is known as a kilonova. These luminous remnants are visible across various wavelengths, from infrared to visible light, allowing astronomers to study these violent cosmic events in unprecedented detail. The sight of such an event confirms the role of neutron-star collisions in the creation of heavy elements, enriching our understanding of nucleosynthesis, the process by which elements are formed in the universe. At the heart of these mergers, the end state can vary dramatically. Depending on the masses of the stars involved, the collision may result in the formation of a more massive neutron star, or if the combined mass is sufficient, a black hole. Groundbreaking observations, such as those of the GW71's AO117 event detected by LIGO and Virgo observatories, have provided invaluable insights into gravitational waves, the behavior of matter in extreme conditions, and the cosmic origins of heavy elements. These discoveries continue to advance our knowledge of the universe, showing us just how interconnected these cosmic phenomena are. In contrast, white dwarf mergers are a fascinating yet different cosmic event. White dwarfs are the remnants of stars that were not massive enough to end their lives in supernovae. Instead, they shed their outer layers, leaving behind a dense core made mostly of carbon and oxygen. When two white dwarfs in a binary system spiral together, the merger can result in a range of outcomes, each as extraordinary as the last. Unlike neutron-star collisions, which often produce gamma-ray bursts and kilonovae, white dwarf mergers can trigger events that are equally significant, but in different ways. If the combined mass of the merging white dwarfs exceeds a critical threshold, around 1.4 times the mass of the Sun, the result can be a Type 1a supernova, a brilliant and powerful explosion that marks the complete destruction of the merged star. This type of supernova is crucial in measuring cosmic distances and understanding the expansion rate of the universe. When a white dwarf merger does not reach the necessary mass for a supernova, however, the process can lead to the formation of a more massive, stable white dwarf. This new star may have an atypical composition, offering scientists new insights into stellar evolution and the dynamics of galaxies. White dwarf mergers also play an important role in galactic chemical enrichment. These events can produce elements such as iron and nickel, which gradually enrich the galaxy over billions of years. In this way, they contribute to the ongoing formation of the elements that make up the planets, stars, and life itself. As a result, the study of white dwarf mergers is vital not only for understanding stellar evolution, but also for improving our ability to measure the cosmic distance scale and refine cosmological models. In addition to the dramatic consequences of neutron star and white dwarf mergers, a magnetar explosion near our solar system would have catastrophic effects. Magnetars are a type of neutron star with magnetic fields thousands of times stronger than those of typical neutron stars. These intense fields can cause the magnetar to undergo violent seismic activity, or starquakes, that release enormous amounts of energy, mostly in the form of gamma rays and X-rays. If such an explosion were to occur within a few light years of Earth, the consequences could be devastating. The burst of radiation could strip away our planet's atmosphere, exposing life on Earth to dangerous levels of radiation, potentially triggering mass extinctions. The potential for such a cosmic event reminds us of the fragile nature of life in the vastness of space and underscores the tremendous forces at work in the universe. These events, from neutron star collisions to white dwarf mergers and magnetar explosions, offer us a glimpse into the incredible, often violent processes that shape the cosmos. As scientists continue to study these phenomena, we are continually reminded of how much we have yet to learn about the universe that surrounds us. The explosion of a magnetar, an incredibly dense remnant of a star that has undergone a supernova explosion, could trigger devastating consequences for Earth. If such an explosion were to occur close enough, the gamma rays emitted might cause chemical reactions in Earth's atmosphere, creating harmful compounds that further degrade the ozone layer. This degradation would leave the planet exposed to the sun's lethal ultraviolet rays, making life on Earth even more vulnerable. Additionally, the explosion could unleash intense magnetic activity capable of inducing electric currents in the Earth's crust and power grids, potentially causing widespread electrical outages and damaging satellites in space. This magnetic disturbance could wreak havoc on electronic systems, leaving humanity scrambling to repair the damage. While the idea of a nearby magnetar explosion seems catastrophic, it also fascinates scientists. Magnetars are among the most energetic objects in the universe, and studying their explosions provides vital insights into the most extreme phenomena in space. Fortunately, the nearest known magnetar is thousands of light years away, offering us a safe distance to observe these celestial wonders without the immediate threat of an explosion. The rare nature of such an event makes it highly improbable, yet understanding magnetars and their behavior is crucial. It helps scientists explore the limits of what can occur in the universe and broadens our knowledge of cosmic environments. In our quest to explore the possibilities of extraterrestrial life, extremophiles, organisms that thrive in Earth's most extreme environments, offer an invaluable clue. These organisms exist in habitats that would be deadly to most other forms of life, from the scalding waters of deep-sea hydrothermal vents to the icy conditions of Antarctica's frozen deserts. What makes extremophiles truly fascinating is their ability to survive in such hostile conditions thanks to specialized biochemical and structural adaptations. Thermophiles, for example, endure boiling temperatures by producing heat-stable proteins and enzymes. Psychrophiles, living in freezing environments, have antifreeze proteins that prevent ice from forming within their cells, ensuring cellular function at sub-zero temperatures. There are also acidophiles, which flourish in extremely acidic environments, and alkaliphiles, which prefer highly basic surroundings. These organisms maintain a balanced internal pH despite the harsh external conditions they face. Radiation-resistant extremophiles, such as D. radiodurans, can repair extensive DNA damage caused by high doses of radiation, making them invaluable models for studying resilience. The ability of extremophiles to adapt and thrive in such extreme environments significantly expands our understanding of life's potential. If life can persist under such conditions on Earth, it opens up exciting possibilities for life existing in similarly harsh environments on other planets or moons. One particularly intriguing possibility lies in the icy moons of Jupiter and Saturn, such as Europa and Enceladus, which contain subsurface oceans heated by tidal forces. These moons, along with Mars and its potential subglacial habitats, are considered prime candidates for the search for extraterrestrial life. The study of extremophiles, in fact, directly informs astrobiological missions seeking life beyond Earth. Their remarkable ability to adapt to extreme conditions inspires hope that life could exist in environments that seem inhospitable, not only within our solar system, but also on exoplanets that lie light years away. Jupiter, the largest planet in our solar system, offers another extreme environment, one unlike anything on Earth. Its atmosphere, primarily composed of hydrogen and helium, is home to powerful storms, including the iconic Great Red Spot, a storm that has been raging for centuries. As you descend deeper into Jupiter's atmosphere, pressures and temperatures increase dramatically, causing hydrogen to undergo a transformation into liquid metallic hydrogen at depths of about 1,000 miles. This unique state of hydrogen is electrically conductive and contributes to the generation of Jupiter's immense magnetic field. Beneath this layer of liquid metallic hydrogen lies a core, believed to be composed of rock and metal, though its exact composition remains a subject of ongoing research. The extreme pressures and temperatures within Jupiter create an environment where materials behave in ways that are fundamentally different from those on Earth. The liquid metallic hydrogen layer is responsible for generating planetary magnetic fields that are thousands of times stronger than Earth's. These magnetic fields influence Jupiter's magnetosphere, contributing to spectacular auroras and playing a key role in the planet's dynamic atmosphere. Understanding Jupiter's internal structure not only expands our knowledge of gas giants, but also provides critical insights into the formation and evolution of our solar system. By studying Jupiter, we gain a better understanding of the processes that shape the planets and their unique characteristics. This knowledge is essential for future space exploration, offering us clues about the conditions that could support life on distant worlds and how those environments might evolve over time. The mysteries of magnetars, extremophiles, and Jupiter are interconnected, each revealing something new about the extremes of the universe and the adaptability of life. In missions like the Galileo orbiter and the Juno spacecraft, scientists have made groundbreaking strides in unraveling the secrets of Jupiter's atmosphere, magnetic field, and interior. These missions have provided crucial data that have expanded our understanding of not only Jupiter, but also of the massive and enigmatic worlds that inhabit our universe. Stars that exist in extreme environments, especially those near supermassive black holes, are subject to intense forces and radiations, making their survival a fascinating testament to the delicate balance of cosmic mechanics. Supermassive black holes, typically located at the centers of galaxies, possess an immense gravitational pull that influences everything in their vicinity. These forces create a region of space where conditions are so extreme that most stars cannot survive. The survival of stars in such harsh environments near black holes is a remarkable phenomenon, illustrating the dynamic and complex interplay of astrophysical processes. The stars that manage to endure near supermassive black holes are often those that maintain stable orbits, typically elliptical. These orbits are crucial as they prevent the star from straying too close to the black hole's event horizon, where even light cannot escape. The forces at work near the event horizon are overwhelmingly destructive, with any star that ventures too close being torn apart by tidal disruption. However, stars that can maintain their position are often aided by gravitational interactions with the other massive objects or nearby stars. This cosmic choreography shepherds them along a safe path, far enough from the destructive forces of the black hole. The mass of both the star and the black hole itself plays a crucial role in this delicate balance. Denser stars, or those with stronger self-gravity, are better equipped to withstand the tidal forces that threaten their existence. Even the densest stars, however, are not immune to the high-energy radiation and gravitational forces present near a supermassive black hole. Over time, the material of these stars can be stripped away, leaving them vulnerable to being consumed by the black hole. Yet, despite these extreme conditions, some stars manage to coexist in the regions near supermassive black holes, known as accretion disks. In these disks, stars interact with dense gas and other stellar material, occasionally even forming new stars from the remnants of collapsed matter. However, these stars often have short lifespans, as the environment around them remains relentlessly hostile. One of the most fascinating examples of stars surviving near a supermassive black hole is the discovery of stars orbiting Sagittarius A, Sirius A, the supermassive black hole at the center of our own Milky Way galaxy. These stars are on tight, rapid orbits, and their behavior provides valuable insights into the workings of matter and gravity in one of the most extreme environments known to science. The study of these stars offers a unique opportunity to test theories of general relativity and to understand the complex interactions that govern galactic centers. Thus, while the environment around supermassive black holes is undoubtedly extreme, the survival of stars in such conditions is a testament to the resilience of stellar objects. Their ability to endure despite the harsh forces at play offers a glimpse into the dynamic processes of the universe's most formidable locales. Understanding these interactions not only expands our knowledge of the cosmos, but also helps us probe the fundamental nature of gravity and matter in some of the universe's most challenging environments. Similarly, the matter surrounding a neutron star experiences conditions beyond anything we could replicate here on Earth. Neutron stars, the remnants of massive stars that have exploded in supernova, pack more mass than the Sun into a volume no larger than a city. The gravitational force near a neutron star's surface is about 10 billion times stronger than that on Earth, which profoundly alters the behavior of matter in its vicinity. At these extreme densities, atoms are crushed, protons merge into neutrons, and the star's core becomes an incredibly dense sphere made almost entirely of neutrons. A mere sugar cube-sized portion of neutron star material would weigh about 1 billion tons here on Earth. The outer crust of a neutron star consists of atomic nuclei arranged in a lattice structure surrounded by a sea of electrons. As we move deeper into the star, the pressure increases, pushing protons and electrons together to form neutrons. In the inner crust, the matter becomes even more exotic, potentially forming superfluid neutrons or superconducting protons. The core itself is one of the most mysterious and debated regions in astrophysics. Some scientists hypothesize that the core could be made of quarks and gluons, or even more exotic particles like hyperons or Bose-Einstein condensates, though the exact nature of this core remains uncertain and is a subject of active research. The intense gravity near a neutron star also leads to some of the most remarkable astrophysical phenomena. Neutron stars are often magnetically charged, and they can emit powerful beams of radiation detectable as pulses. These beams sweep across the Earth, giving us an unprecedented view into the behavior of matter under extreme gravitational forces. Studying neutron stars and their gravitational effects allows scientists to gather essential data about nuclear physics, that ultra-high-density matter, and the fundamental properties of gravity itself. In summary, the extreme conditions near neutron stars push matter into states that challenge the very boundaries of physics as we know it. The forces at play, both gravitational and magnetic, create environments that can transform matter in ways that are still not fully understood. As we continue to explore these extreme environments, we gain vital insights into the fundamental workings of the universe, helping us answer some of the most profound questions in science. Extremophiles, organisms that thrive in Earth's most extreme environments, have forever altered our perception of life's boundaries. These remarkable creatures inhabit places once thought utterly uninhabitable, including the boiling hydrothermal vents on the ocean floor, the scorching acidic hot springs, and even the freezing sub-zero lakes buried deep beneath Antarctica's ice sheets. Their survival in such hostile conditions challenges our fundamental understanding of life, demonstrating its astonishing resilience and versatility. What makes these organisms so extraordinary is their ability to endure conditions that would obliterate most forms of life. From the extreme heat of geothermal vents to the acidic waters of hot springs, extremophiles prove that life doesn't need warmth or comfort to thrive. In fact, the very environments they inhabit were once thought to be completely devoid of life. Yet, these tenacious organisms survive and in some cases even flourish under conditions that would send most life forms into a rapid decline. These extraordinary adaptations open doors to entirely new possibilities for life beyond our planet. For example, scientists have discovered bacteria surviving and even multiplying in the intense radiation and frigid cold of Earth's deserts or deep within the crust. This revelation sparks intrigue about the potential for life on planets and moons with similarly harsh conditions, such as Mars. Researchers now believe that Mars, with its cold, barren surface and icy caps, may still harbor life, just waiting to be uncovered beneath its surface. Similarly, the ability of certain microbes to metabolize sulfur and other chemicals in Earth's scalding hot springs offers tantalizing clues about the types of biochemical processes that may be occurring in distant icy moons like Europa, one of Jupiter's moons, and Enceladus, Saturn's moon. These moons are thought to harbor subsurface oceans that could contain environments similar to those on Earth, where life could potentially exist under extreme pressure and in the absence of sunlight. Astrobiologists are particularly captivated by the biochemical adaptations that allow extremophiles to thrive under these severe conditions. By studying the molecular mechanisms, such as specialized proteins and enzymes that protect extremophiles' cellular structures, scientists gain valuable insights into the resilience of life in extreme environments. This research is pivotal, as it allows space missions to be better equipped to search for life on distant worlds. Instruments designed to detect life are now being tailored to look for the subtle signs of life that might be hiding in the most extreme and seemingly hostile environments across the cosmos. By mapping the preferences and survival mechanisms of these remarkable organisms, scientists are identifying potential habitats on other planets and moons, such as Europa, Enceladus, and even exoplanets far outside our solar system. Their findings suggest that life, if it exists beyond Earth, may not need temperate, stable environments like our own. Instead, it could thrive in places we've only begun to dream of, challenging the very definition of what it means to be alive in the universe. This groundbreaking research has transformed how we approach the search for extraterrestrial life, expanding our search to places we might never have considered before. It shows us that life, in all its complexity, might be far more adaptable and widespread than we ever imagined. If life can survive in the boiling depths of Earth's oceans or beneath the frozen surface of Antarctica, could it also exist on distant worlds, hidden away in the dark, icy seas of moons millions of miles away? The quest to find life beyond Earth has taken on a new urgency, as we now look at the cosmos through an entirely different lens. Meanwhile, coronal mass ejections, CMEs, from our sun, massive bursts of solar wind and magnetic fields rising above the solar corona, offer a striking reminder of the dynamic forces at play in the universe. These colossal solar events are driven by the sun's magnetic field and represent some of the most energetic phenomena in our solar system. Despite the sun's serene appearance, its atmosphere is anything but calm. Magnetic field lines twist and tangle, building stress over time, until they suddenly snap and reconfigure in a process known as magnetic reconnection. This reconnection releases an enormous amount of energy, propelling solar material outward at astonishing speeds. When a CME is directed towards Earth, it can wreak havoc on our planet's magnetic field, causing geomagnetic storms. These storms can disrupt satellite communications, interfere with radio transmissions, and even affect GPS and other navigation systems, potentially causing widespread disruptions across the globe. As these events continue to reveal the intricate and powerful nature of our sun's behavior, they also highlight the importance of understanding cosmic phenomena. Studying these solar storms provides valuable insights into how space weather impacts our planet and how we can better prepare for the future. With advancements in space research, humanity is learning to anticipate and mitigate the effects of these solar eruptions, ensuring the continued safety and functionality of the technologies we rely on every day. Moreover, the solar activities we witness, particularly the powerful coronal mass ejections, CMEs, can trigger disruptions that ripple through space and impact life here on Earth. When a CME occurs, it sends a wave of charged particles racing toward our planet, creating electrical currents that can overload power grids. This disruption, in turn, sometimes leads to massive power outages, affecting everything from daily conveniences to essential services. It's a reminder of how interconnected our technology is with the environment around us. One of the most captivating effects of a CME is the way it enhances auroras, more commonly known as the northern and southern lights. These vibrant light displays are typically confined to the polar regions of the Earth, where the planet's magnetic field channels solar particles toward the poles. However, during a CME, these mesmerizing lights grow far more intense and can even be visible at much lower latitudes than usual, offering a breathtaking visual reminder of the sun's dynamic relationship with our planet. But while CMEs paint the sky with dazzling lights, they pose a far more serious threat to satellites and astronauts in space. The heightened radiation from a CME can wreak havoc on sensitive electronics, causing potential malfunctions. For astronauts, this influx of energetic particles presents serious health risks. To mitigate these dangers, space agencies like NASA are constantly monitoring solar activity, issuing early warnings when a CME is detected heading toward Earth. With advanced technology and careful preparedness, we can better safeguard both our technological infrastructure and the brave explorers venturing into space. Solar flares, akin to massive explosions on the sun's surface, are another major player in these space weather events. These flares release tremendous amounts of energy, including radiation and energetic particles. When directed toward Earth, these solar bursts interact with the planet's magnetic field and atmosphere, triggering a series of disruptions, especially in our communication networks. For instance, solar flares can disturb the ionosphere, a critical layer of the Earth's atmosphere responsible for reflecting radio waves. High-frequency radio signals, vital for aviation, maritime communication, and emergency services, can experience blackouts, potentially leading to a loss of crucial data and confusion in critical operations. But the impacts of solar flares don't end there. They also threaten the satellites that orbit Earth. The intense radiation can damage or degrade the delicate electronics and solar panels aboard these satellites, potentially resulting in the loss of services like GPS navigation and satellite communication. This is particularly concerning as many activities we take for granted, airline navigation, personal navigation devices, and even financial transactions that rely on precise timing, depend on the functionality of satellites. In addition to communication and navigation, solar flares also pose significant threats to power grid infrastructure. Energetic particles from these flares generate geomagnetically induced currents that can overwhelm and damage transformers and other components of the electrical grid. In severe cases, this surge can cause widespread power outages, with repairs often taking considerable time and resources. The ripple effect disrupts daily life and economic activities on a global scale. As we become more dependent on advanced technology and interconnected systems, our vulnerability to solar flares grows. With each passing year, as we venture further into space and expand our technological reach, understanding and mitigating the effects of solar flare activity becomes increasingly important. That's why ongoing solar monitoring and the development of robust protective measures are high priorities for scientists and engineers around the world. Then, there's the coronal heating problem, a long-standing enigma in solar physics. This mystery involves the inexplicable phenomenon where the sun's outer atmosphere, known as the corona, is far hotter than its visible surface, the photosphere. The photosphere burns at a relatively cool 6,000 degrees Celsius, yet the corona reaches a staggering temperature between 1 to 3 million degrees Celsius. This dramatic temperature difference presents a challenge for scientists to understand. One hypothesis points to magnetic field interactions as the culprit. The sun's magnetic field is constantly in motion, twisting, tangling, and reconfiguring due to the turbulent motions deep within the solar interior. A theory called magnetic reconnection suggests that when these tangled magnetic field lines snap and reconnect, they release immense amounts of energy, which heats up the surrounding coronal plasma. Another intriguing possibility involves alpha waves, named after Swedish physicist Hannes Alf Venn. These waves travel along the sun's magnetic field lines and could carry energy from the turbulent layers beneath the photosphere into the corona. When these waves dissipate, their energy might provide the necessary heat to explain the corona's high temperatures. Observations from spacecraft like NASA's Solar Dynamics Observatory and the Parker Solar Probe are essential for studying these waves and their potential role in coronal heating. Though considerable progress has been made, scientists are still actively researching the exact mechanisms behind this mysterious phenomenon. By combining observational data, theoretical models, and computer simulations, they are working tirelessly to unlock the secrets of the sun's behavior. Understanding the coronal heating problem is not just vital for solar physics, it also has broader implications for astrophysics as a whole. The insights gained from this research could illuminate the behavior of stellar atmospheres across the cosmos, providing clues about the nature of other stars and their interactions with surrounding environments. As we continue to explore the mysteries of the sun and space, the interplay between solar phenomena and our technology remains a fascinating yet daunting reality. Yet with ongoing research, monitoring, and technological advancements, we are better equipped to navigate this complex relationship and protect our world from the sun's immense power. Cosmic radiation, particularly during solar storms and flares, can have a profound impact on air travel. These high-energy particles, which originate from the sun, distant galaxies, and even beyond, can permeate the Earth's atmosphere when solar activity intensifies. This influx of cosmic rays is especially significant during solar flares or coronal mass ejections, events that send powerful bursts of radiation into space. As a result, cosmic ray exposure increases, presenting several potential challenges for aviation. At high altitudes, where commercial planes typically cruise, the atmosphere is thinner, providing less protection from these rays compared to sea level. As a consequence, air crews and passengers flying along high latitude or polar routes, where cosmic ray exposure is naturally higher, are particularly vulnerable during these solar events. Increased exposure to these cosmic rays can lead to higher doses of radiation, which could potentially affect the health of frequent flyers and flight crews over time. To mitigate these risks, regulatory bodies monitor radiation levels closely. Airlines also take proactive measures, sometimes adjusting flight paths or altitudes to reduce exposure during periods of intense solar activity. These solar events, however, don't only affect radiation levels. They can also interfere with avionics, vital electronic systems that control and navigate aircraft. The high-energy particles can cause transient errors, known as single-event upsets in these sensitive components. While modern aircraft are designed to be robust against such interferences, these events highlight the necessity for constant testing and resilience in avionics systems. Moreover, increased radiation in the atmosphere can disturb high-frequency radio communications, which are critical for air traffic control, particularly over remote or oceanic regions where radar coverage is absent. In these cases, alternative communication methods, such as satellite communications, may be necessary. But these too can face challenges when solar activity intensifies. In response to these issues, space weather monitoring stations continuously track solar activity. Real-time data, combined with predictive models, allows for timely alerts to the aviation industry, giving airlines the ability to make informed decisions and ensure the safety of air travel. This intricate connection between space phenomena and terrestrial technology underscores the need for vigilance and adaptation in our increasingly interconnected world. One fascinating aspect of solar activity is the reversal of the sun's magnetic field, an event that occurs roughly every 11 years. This phenomenon is driven by complex dynamics within the sun's interior and is a crucial component of solar activity, influencing everything from sunspots to solar flares and coronal mass ejections. During this reversal, the sun's north and south magnetic poles switch places, initiating a series of events that profoundly affect the solar system. At the core of this magnetic flip lies the sun's dynamo mechanism. Located deep within the sun's convective zone, this area experiences turbulent convective motions where hot plasma rises, cools, and then sinks. Combined with the sun's rotation, these motions generate the sun's magnetic field. The process is known as the alpha-omega dynamo. The differential rotation of the sun, where the equator rotates faster than the poles, stretches and twists magnetic field lines, creating large-scale magnetic structures visible on the sun's surface. Simultaneously, turbulent convection twists and shears these field lines, amplifying the magnetic field. As the solar cycle progresses, sunspots, temporary phenomena linked to the sun's magnetic field, become more numerous, migrating toward the equator. These sunspots mark the peak of solar activity, known as the solar maximum. It is during this time that the magnetic field is at its most dynamic, and the poles eventually swap places. Once this process completes, the cycle enters a period of waning solar activity, known as the solar minimum, before the magnetic field resets itself in preparation for the next reversal. This continuous dance of magnetic forces within the sun has captivated scientists for decades, spurring ongoing research to better understand the underlying mechanisms and predict future solar activity. The implications of the solar cycle extend far beyond scientific curiosity. They influence space weather, satellite operations, and even Earth's climate. Understanding these processes is critical, highlighting the importance of continued monitoring and study of our closest star. Equally captivating are molecular clouds, often referred to as stellar nurseries. These vast, dense regions of gas and dust are the birthplaces of new stars. Composed mainly of molecular hydrogen, molecular clouds are scattered across galaxies and represent the raw material from which stars are formed. The process of star birth is an intricate journey, driven by the forces of gravity and thermodynamics. It begins when a portion of a molecular cloud becomes unstable. This instability can arise from various disturbances, such as shock waves from nearby supernova, stellar winds, or interactions with other clouds. These disruptions compress the gas and dust, causing regions within the cloud to reach higher densities. Once these regions, known as clumps, become dense enough, the force of gravity overcomes the internal pressure holding them up, initiating further collapse. As this clump collapses under its own gravity, the journey of star formation begins. The birth of a star is one of the most extraordinary processes in the universe. It begins in the vast, dark regions of molecular clouds, where gravity pulls gas and dust together into denser clumps. As these clumps collapse under their own gravity, they fragment into smaller, increasingly dense cores. The pressure and temperature within these cores rise rapidly, and when the center becomes hot and dense enough, nuclear fusion ignites. This fusion process converts hydrogen into helium, releasing an immense amount of energy and signaling the birth of a new star. This early phase is known as the protostar stage, marking the beginning of a star's journey through the cosmos. During this stage, the protostar continues to gather material from its surrounding gas and dust. As this material spirals inward, it forms a rotating disk, known as an accretion disk. The accretion disk is a dynamic and vibrant region where new celestial bodies, such as planets and moons, are born. As the protostar stabilizes, it clears its environment through the force of radiative pressure and stellar winds, gradually revealing a star that begins to shine brightly. This marks the transition to the main sequence phase, where nuclear fusion in the core is balanced, and the star enters its long, stable phase of life, shining for billions of years. However, like everything in the universe, a star's life is not eternal. The fate of a star depends largely on its mass. When stars like our sun near the end of their lives, they exhaust the nuclear fuel in their cores. Without the energy produced by fusion, the core contracts and heats up, while the outer layers expand and cool. This transformation turns the star into a red giant. As the outer layers of the giant star become increasingly unstable, they are ejected into space by powerful stellar winds, leaving behind a hot, dense core known as a white dwarf. Despite its small size compared to its former self, the white dwarf radiates intensely in ultraviolet light, which illuminates the surrounding expelled gas. This glowing gas forms what is known as a planetary nebula, an often vibrant and colorful shell of gas and dust that represents the final act of a star's life. The light emitted from a planetary nebula is caused by a process called photoionization, where ultraviolet radiation from the white dwarf excites the gas, causing it to glow. The emission of hydrogen results in a red or pink glow, while ionized oxygen creates striking green and blue hues. These glowing shells are not only beautiful spectacles, but are also key to understanding the complex dynamics of stars as they near their end. The shapes of planetary nebulae can range from spherical to bipolar, offering astronomers important clues about how stars shed their outer layers, as well as about the interactions between the stellar material, magnetic fields, and any companion stars. The planetary nebula is a final gift to the cosmos. The elements expelled into space enrich the interstellar medium, contributing to the formation of new stars and planets, including the raw materials necessary for life. The light of these nebulae serves as a poignant reminder of the cyclical nature of the universe, where even in death, stars give birth to new worlds. Yet, the death of a massive star is even more dramatic. When a star of greater mass runs out of nuclear fuel, it explodes in a spectacular supernova. This explosion is an incredible event, releasing vast amounts of energy and scattering the star's outer layers into space at speeds of millions of kilometers per hour. The shock wave created by the explosion compresses and heats the surrounding interstellar medium, creating a bright, energetic remnant known as a supernova remnant. Initially, this remnant is dominated by the shock wave, which expands outward, heating the surrounding gas and emitting light across multiple wavelengths, including X-rays, visible light, and radio waves. As the remnant continues to expand, it enters a phase where it is no longer influenced primarily by the initial explosion, but by the surrounding interstellar medium. This transition marks the beginning of the snowplow phase, where the expanding shockwave slows and begins to interact more complexly with the material it encounters. During this phase, the remnant glows less brightly but continues to shape the surrounding space with intricate filamentary structures. Over time, the remnant cools and merges with the interstellar medium, eventually dispersing the heavy elements, such as iron and silicon, into the surrounding space. These elements will go on to form future generations of stars and planets, and perhaps even the building blocks of life itself. In this endless cycle, stars give and take from the cosmos, transforming the universe with their brilliant beginnings and dramatic ends. From the birth of a protostar to the explosive final moments of a supernova, these celestial events tell the story of life and death in the universe, one that is both humbling and awe-inspiring. Through the lens of modern telescopes and space missions, we continue to uncover these cosmic mysteries, gaining a deeper understanding of the forces that shape the stars, our sun, and the vast universe we call home. The evolution of supernova remnants offers us invaluable insights into the life cycles of stars, the complex dynamics of the interstellar medium, and the process by which galaxies are enriched with heavy elements. Astronomical observations gathered from telescopes across a broad range of wavelengths are continually unveiling the detailed and intricate workings of these celestial phenomena. These observations show the immense forces at play and the staggering processes that govern the cosmos. The interstellar medium, ISM, is an enormous, often enigmatic expanse of gas dust and cosmic rays that fills the vast space between the stars within a galaxy. While this region might appear empty, it is anything but. The ISM is a crucial component in the life cycle of stars and the evolution of galaxies, playing a central role in both. Despite being sparsely populated, the ISM is remarkably rich in components, each with distinct contributions to the cosmic environment. At its core, the ISM is primarily composed of hydrogen and helium, along with small traces of heavier elements, also known as metals in astronomical terms. These metals are remnants of past stellar processes, such as supernova explosions and powerful stellar winds, which have seeded the ISM with heavier elements over time. The gas that makes up the ISM exists in various physical states, ranging from cold, dense molecular gas to hot, diffuse ionized gas. The temperature, density, and ionization state of this gas can vary dramatically, leading to the formation of different phases within the ISM. One of the most essential components of the ISM is molecular clouds, which are cold and dense regions often referred to as stellar nurseries. These clouds, composed mainly of molecular hydrogen, are significantly more massive than the Sun and serve as the raw material from which stars are born. On the other hand, the ISM also contains hot, ionized gas, which exists at temperatures reaching millions of degrees Kelvin. This hot gas fills the lower density regions of the ISM, known as the intercloud medium. Supernova remnants and massive stars contribute to this hot gas through their energetic outputs. In addition to gas, interstellar dust, tiny solid particles composed of elements like carbon, silicon, and iron, forms another crucial part of the ISM. Despite making up only about 1% of the ISM by mass, this dust plays an essential role in astrophysical processes. It absorbs and scatters light, contributing to the dark patches and stunning colors seen in nebulae. Additionally, interstellar dust is involved in the formation of molecules, such as molecular hydrogen, on its surfaces. It serves as the building blocks for planets when new star systems emerge. The interactions within the ISM, including those between gas, dust, and cosmic rays, result in a dynamic and constantly evolving medium. Shock waves generated by supernovae, stellar winds, and other energetic processes continually shape the ISM, molding its structure and facilitating the ongoing cycles of star formation and destruction. By studying the ISM, astronomers gain valuable insights into the processes behind the birth of stars and planets and the large-scale structure and evolution of galaxies. The ISM is, in essence, the cosmic framework that enables the formation and destruction of stars and galaxies, profoundly shaping the universe as we know it. One particularly intriguing phenomenon within the ISM is the formation of bow shocks. These structures occur when a star, particularly one moving at high speeds through the interstellar medium, creates a region where its stellar wind interacts with the surrounding gas and dust. This process is similar to the bow wave created by a ship moving through water. When a star produces a bow shock, its stellar wind, streams of charged particles emitted by the star, collides with the interstellar medium. This collision compresses and heats the gas, resulting in a distinctive curved shock front. The power of a star's stellar wind determines the shape and intensity of the bow shock. If the stellar wind is strong enough to push against the interstellar medium, the shock front forms a bow-like structure around the star. At the boundary of this shock front, where the stellar wind slows abruptly, lies the termination shock. The outermost edge of the bow shock, where the shock front meets the undisturbed interstellar medium, is known as the bow shock itself. Between the termination shock and the bow shock lies a region filled with turbulent, compressed gas, called the astrosheath. Bow shocks have been observed around massive, luminous stars such as O-type and B-type stars, as well as older pulsars moving at high velocities. These observations are often made in infrared wavelengths where the heated gas and dust emit strongly. The shape and size of these bow shocks offer astronomers valuable clues about a star's velocity, the strength of its stellar wind, and the nature of the surrounding interstellar medium. Studying these structures provides a deeper understanding of stellar motion and interactions within the interstellar medium, revealing the intricate relationship between stars and the cosmic material they interact with. Furthermore, gravitational lenses offer a fascinating glimpse into distant regions of the universe, allowing us to observe galaxies that would otherwise be nearly impossible to see. These cosmic lenses, created by the bending of light around massive objects like galaxy clusters, enable astronomers to peer into the farthest reaches of space and uncover hidden celestial wonders. Through the study of gravitational lenses and other cosmic phenomena, we continue to unlock the mysteries of the universe, expanding our understanding of the vast and awe-inspiring forces that govern the cosmos. In this exploration of cosmic phenomena, we delve deep into one of the most awe-inspiring phenomena in modern astrophysics: gravitational lensing. This concept taps into the power of gravity to not only warp light, but to reveal previously inaccessible regions of space and time. It is a prediction first made by Albert Einstein in his theory of general relativity, and it has since been confirmed through decades of astronomical observations. Gravitational lensing occurs when a massive object, such as a galaxy or even a galaxy cluster, positions itself between a distant source of light and our vantage point on Earth. The immense gravitational field of this object acts like a lens, bending and magnifying the light that passes through it. Imagine light as a stream traveling through space. As it nears a large object, the object's gravity bends the light paths inward. This phenomenon is remarkably similar to how a glass lens bends light, except the effects are on a cosmic scale. As the light bends, its path is altered, which can lead to the magnification of distant objects, often making them appear brighter or more defined. In some cases, this bending effect is so strong that it splits the light into multiple images of the same object. The objects responsible for causing this distortion are called gravitational lenses, and the distorted, magnified light that we see is referred to as the lensed source. The complexity of gravitational lenses varies, from strong lenses that create dramatic arcs and multiple images, to weaker lenses that subtly distort the appearance of distant galaxies. The most stunning of these gravitational lensing effects occurs when what we call an Einstein ring is formed. This phenomenon happens when the light from a lensed galaxy is bent so perfectly around the gravitational lens that it forms a complete ring of light encircling the lensing object. These Einstein rings are not just beautiful to observe, but they also offer a critical advantage to astronomers, providing a powerful tool for observing galaxies and other cosmic structures that would otherwise be unreachable by even our most advanced telescopes. These distant galaxies, often formed in the earliest epochs of the universe, hold essential clues to the formation and evolution of the cosmos. One of the most profound aspects of gravitational lensing is its potential for studying dark matter. While dark matter cannot be seen directly, its gravitational influence on visible matter is undeniable. By analyzing the distortions caused by gravitational lenses, scientists can infer the presence and distribution of dark matter within lensing galaxies, or galaxy clusters. This remarkable ability to study dark matter provides an unprecedented look into one of the greatest mysteries of the universe. Through the lens of gravitational lensing, we are granted a view into the farthest reaches of space, able to peer back in time and uncover secrets that have been hidden for eons. This phenomenon is a perfect embodiment of the elegance of general relativity and the endless human curiosity to explore the distant universe. It is through such extraordinary events that we continue to push the boundaries of our understanding of the cosmos. At the forefront of this exploration is the James Webb Space Telescope, JWST, a transformative tool designed to observe the early universe with unmatched precision. What sets the JWST apart is its ability to detect infrared light, a vital feature that allows it to peer through cosmic dust clouds and capture the faint, ancient light from the earliest galaxies and stars. The universe's expansion causes light from these early objects to shift from visible to infrared wavelengths due to the redshift effect, and the JWST is specifically designed to capture this faint shifted light. One of the most impressive aspects of the JWST is its enormous primary mirror, which is over 6 times larger in area than the Hubble Space Telescopes. This massive mirror is made up of 18 hexagonal segments coated in gold to enhance its reflectivity, allowing the telescope to gather more light and peer further back into the past than ever before. This incredible size gives the JWST an unmatched ability to capture distant, faint light, opening new windows into the universe's early history. In addition to its powerful mirror, the JWST's location and cooling system are pivotal to its success. Orbiting around the second Lagrange point, 1.5 million kilometers from Earth, the telescope operates in a stable, interference-free environment. This unique position allows the telescope to stay in constant communication with ground control while being shielded from the sun by a sophisticated sun shield. This cooling mechanism ensures that the telescope's instruments remain at extremely low temperatures, allowing them to detect the faint infrared signals from distant objects without interference from the telescope itself. Equipped with 4 cutting-edge scientific instruments, cameras, spectrographs, and coronagraphs, the JWST is able to conduct detailed imaging, spectroscopy, and study the physical properties of celestial objects. With the JWST, scientists can investigate the early universe, the formation of stars and planets, and even examine the properties of primordial galaxies. This is a true leap forward in our ability to study the cosmos, giving us the tools we need to uncover the universe's most profound secrets. Through the combined powers of gravitational lensing and the JWST, we are embarking on a new era of astronomical discovery, one that promises to answer questions we've only just begun to ask about the nature of the universe, its formation, and the forces that govern it. Exoplanet atmospheres and the chemical compositions of distant galaxies are at the frontier of modern astronomy. With the groundbreaking advancements in technology, the study of these celestial phenomena has entered a new era. The James Webb Space Telescope, JWST, harnesses these innovations, propelling itself far beyond the capabilities of previous telescopes. It is not just observing distant stars and galaxies, but unveiling the deepest layers of the universe, offering us unprecedented clarity and insight. By gazing into the early cosmos, the JWST aims to answer fundamental questions about cosmic origins, the evolution of galaxies, and the mysterious nature of dark matter. It promises to offer us a compelling, near-mystical glimpse into the earliest epochs of the universe, bringing the cosmos to life like never before. One of the most transformative techniques in astronomical observation today is very long baseline interferometry, VLBI. VLBI is a remarkable method that combines the power of multiple radio telescopes, each located across vast distances, to create a single giant virtual telescope. The baseline, the virtual distance between these telescopes, can stretch across continents, sometimes even incorporating space-based antennas. This immense distance creates an observation capability that provides astonishingly high resolution, enabling astronomers to observe objects in the universe with a level of detail once thought impossible. Through synchronization, VLBI coordinates these telescopes to capture faint radio waves emitted by distant celestial objects, such as galaxies, quasars, and remnants of supernovae. Radio waves, however, are weak and travel vast distances. As they make their journey through space to each telescope, they arrive slightly out of sync due to the finite speed of light and the separation between the telescopes. To precisely capture this data, each telescope is equipped with highly accurate atomic clocks, often hydrogen masers, ensuring that the time of arrival of each signal is measured down to nanoseconds. Once this data is captured, it is sent to a central facility known as a correlator, where the signals are aligned according to the time differences. This meticulous process creates interference patterns, which astronomers then use to construct high-resolution images, allowing them to study celestial phenomena with precision comparable to having a telescope as large as the distance between the participating radio telescopes. VLBI's strength lies in its ability to achieve extraordinary angular resolution. This capability allows scientists to peer into the smallest, most distant corners of the universe, mapping and studying phenomena like never before. One of the most extraordinary successes of VLBI has been its role in capturing the first ever image of a black hole's event horizon through the collaboration of a global VLBI network known as the Event Horizon Telescope. The technique has also enabled detailed studies of the dynamics of quasars, the distribution of matter in galaxies, and our understanding of pulsars and other compact objects. By overcoming the physical limitations of individual radio telescopes, VLBI has given humanity a window into the most enigmatic and far-flung objects in the cosmos, transforming our understanding of the universe. Neutrino detectors, often referred to as the ghost particles of the universe, offer a profound insight into the core processes of stars, particularly our sun. Neutrinos are subatomic particles that are produced during nuclear reactions, like the ones that power the sun. Because neutrinos interact very weakly with matter, they can escape from the sun's core and travel through space largely unaffected. This makes them exceptional messengers, carrying direct information about the intense conditions deep within the sun. Neutrino detectors on Earth, such as the Super Kamiokande in Japan and the Sudbury Neutrino Observatory in Canada, are designed to capture these elusive particles. When neutrinos interact with the detecting material, usually a massive volume of water or heavy water, they produce faint flashes of light, known as Cherenkov radiation. Sensitive instruments are able to detect these flashes, allowing scientists to count neutrino interactions and analyze their properties, such as their energy and flavor. By studying the flux and characteristics of these solar neutrinos, researchers can test and validate models of solar fusion and energy production. The standard solar model predicts specific neutrino production rates and energy distributions from different fusion reactions occurring in the sun's core. The study of these particles is allowing us to understand the very heart of our star, providing crucial data that reinforces our understanding of solar dynamics and nuclear fusion processes. In both cases, from the high-tech capabilities of VLBI to the groundbreaking detection of neutrinos, technology is enhancing our ability to explore the cosmos in ways once thought impossible. These advances not only deepen our understanding of the universe, but also serve as a testament to human ingenuity in the face of the unknown. With every discovery, we inch closer to unlocking the universe's greatest mysteries. Neutrinos are often referred to as ghost particles because of their elusive nature and their ability to pass through matter without interacting. Yet, observing them directly has provided some of the most profound insights into the workings of the sun, confirming our understanding of the nuclear reactions that convert hydrogen into helium, the primary energy source for the sun. One of the most groundbreaking revelations from early neutrino detection experiments was the discovery of a discrepancy between the predicted and observed neutrino flux, a mystery known as the solar neutrino problem. Initially, scientists were perplexed by the absence of the expected number of neutrinos, but this puzzle was eventually solved with the realization that neutrinos can oscillate between different flavors, electron, muon, and tau, as they travel from the sun to Earth. This phenomenon of neutrino oscillation provided the critical evidence that neutrinos have mass, which radically altered our understanding of particle physics. Before this discovery, the standard model of particle physics did not account for neutrino mass. As a result, neutrino detectors became a valuable tool not only in studying the sun's core, an area otherwise inaccessible to direct observation, but also in deepening our understanding of the universe at the fundamental particle level. These detectors have confirmed theoretical models of stellar energy production, furthering our knowledge of how stars like the sun shine. In addition, ongoing advancements in neutrino detectors and astronomical techniques have opened up new frontiers in astrophysics, offering fresh insights into other celestial phenomena and contributing to groundbreaking discoveries in particle physics. As we continue to refine our understanding of the cosmos, one of the most exciting technological advancements has been the development of adaptive optics systems. These systems are crucial in overcoming the blurring effects caused by Earth's atmosphere. When light from distant celestial objects passes through the atmosphere, it becomes distorted by shifting air currents and varying temperatures. This turbulence causes stars to twinkle and makes images from ground-based telescopes appear fuzzy. Adaptive optics work by using a series of flexible mirrors that can adjust their shape in real time, compensating for the distortions caused by the atmosphere. These mirrors are controlled by computers that analyze the incoming light, detecting distortions and adjusting the mirrors multiple times per second to cancel out the effects of the turbulence. The result is a much sharper, clearer image of distant stars, galaxies, and other celestial phenomena, clarity that was once only possible with space-based telescopes. This technology has revolutionized ground-based astronomy, enabling astronomers to explore the universe with unprecedented precision. Features such as the formation of stars and nebulae or intricate details on exoplanets, which were previously hidden, can now be observed in stunning detail. Adaptive optics have thus opened new doors for astronomical research, advancing our understanding of the cosmos and allowing us to peer deeper into the universe than ever before. On a different front, planetary protection efforts are essential for safeguarding Mars from the contamination of Earth's microbes during exploration. This meticulous process ensures that the Martian environment remains pristine for scientific study, preserving its natural state and preventing interference with the search for potential indigenous life. Achieving this requires a series of rigorous sterilization procedures for any spacecraft destined for Mars. Every component of the spacecraft must be carefully cleaned and, when possible, sterilized using techniques such as heat, radiation, or chemical treatments. To minimize microbial presence, spacecraft assembly occurs in ultra-clean facilities with advanced air filtration systems and strict cleanliness protocols. Once the spacecraft is assembled, additional sterilization measures are often necessary. For instance, some parts may undergo dry heat microbial reduction, a process that involves subjecting components to elevated temperatures to eradicate any remaining microorganisms. These procedures ensure that even the most resilient microbes are significantly reduced, preserving Mars in its natural state for future exploration and preventing contamination that could alter scientific results. This attention to detail is vital in maintaining the integrity of Mars exploration, ensuring that any discoveries made on the Red Planet are not tainted by our earthly presence. In the pursuit of venturing beyond our home planet, scientists have taken immense strides in ensuring that humanity's exploration of Mars and beyond is conducted with the utmost care. A crucial component of this effort is the constant monitoring and cataloging of microbial contamination on spacecraft. Using sophisticated detection techniques, scientists meticulously assess contaminant levels, ensuring that these spacecraft remain uncontaminated. This level of precision is paramount, as it guarantees that when humanity finally reaches Mars, we are not inadvertently introducing Earth's microbial life into its potentially habitable environment. By preserving the integrity of Mars's pristine conditions, we open the door for unbiased, uncontaminated scientific discoveries, providing us with valuable insights into the planet's true nature. Yet the excitement of space exploration is far from without its challenges. Asteroid mining, a concept once relegated to the realm of science fiction, now looms on the horizon as a potential frontier for resource acquisition. However, the technical and logistical hurdles that must be overcome are substantial. The The sheer distance between Earth and asteroids is staggering, often reaching millions of miles, and this isolation presents significant challenges in terms of both travel and resource management. Spacecraft capable of enduring such long-duration missions are essential, requiring robust propulsion systems and precise navigation to ensure that they can accurately reach their moving targets in the vast expanse of space. Once an asteroid is reached, the real complexity begins. The very low gravity of these celestial bodies presents a unique set of obstacles. Traditional mining techniques, which rely on gravity to stabilize equipment, simply do not work in such an environment. Instead, specialized anchors or thrusters will likely be required to keep mining machinery in place. The machinery itself must also be engineered to withstand the harsh vacuum of space, where extreme temperatures and radiation are constant threats to functionality. Furthermore, material processing presents another hurdle. Extracted resources will either need to be processed in situ or transported back to Earth or another off-planet location, requiring advanced autonomous systems capable of operating without human intervention. The energy requirements for such operations are significant, necessitating advanced power sources like solar arrays or nuclear reactors to power the entire process. In addition to these technical challenges, asteroid mining raises complex legal and ethical questions. The 1967 Outer Space Treaty, signed by many countries, prohibits national appropriation of celestial bodies. This legal framework creates a gray area when it comes to determining who owns and has rights to resources mined from asteroids. It's clear that new international cooperation, regulations, and agreements will be needed to ensure the fair and sustainable use of these valuable extraterrestrial resources. Shifting focus to another monumental endeavor, terraforming Mars. This challenge is equally monumental, involving vast scientific and engineering feats that are yet to be realized. Mars, with its thin, carbon dioxide-dominated atmosphere and lack of breathable oxygen, presents a hostile environment for human habitation. The first step in transforming the Martian atmosphere into something more suitable for human life is to release trapped gases from the planet's surface and ice caps, thickening the atmosphere and creating a greenhouse effect. Gases like perfluorocarbons could help retain heat, potentially initiating a runaway greenhouse effect that raises both the atmospheric pressure and temperature, bringing Mars closer to conditions suitable for human life. Creating liquid water on the surface of Mars is another key step in this process. Currently, water exists on Mars primarily as ice at the poles and beneath the surface. To create bodies of liquid water, the planet's temperature would need to be raised significantly. This presents both an opportunity and a challenge. Once liquid water exists, it could support life and make agriculture possible, which is essential for human colonization. However, preventing the water from refreezing and maintaining a stable, usable supply would require continuous effort and ingenuity. Another challenge that looms large in the process of terraforming Mars is the creation of breathable oxygen. Various methods have been proposed, including using photosynthetic organisms like algae or leveraging advanced technology to electrolyze water, splitting it into oxygen and hydrogen. Once a reliable method for oxygen production is developed, humans could begin to create controlled habitats with breathable air. Over time, these habitats could be expanded as more oxygen is produced and stored, allowing for larger human colonies to flourish on the Martian surface. These incredible scientific and engineering challenges represent just the tip of the iceberg in humanity's quest to explore and colonize other planets. However, they offer a tantalizing glimpse into a future where the stars may no longer be out of reach. Protecting Mars from the harsh effects of solar and cosmic radiation remains a critical challenge due to the planet's lack of a magnetic field, which Earth benefits from. This radiation could severely hinder any attempt at long-term human habitation on the red planet. To overcome this, scientists and engineers are proposing large-scale projects, such as constructing magnetic shields around Mars or creating subterranean habitats. These ideas are not just ambitious, they are fraught with scientific and logistical difficulties. Yet, the thought of transforming Mars into a habitable world sparks the imagination and propels humanity forward in its pursuit of space colonization. However, while the physical barriers of space exploration pose significant challenges, the psychological toll of long-duration space travel is equally formidable. Astronauts face immense psychological hurdles, including isolation, confinement, and prolonged separation from Earth. The intense solitude of space can be emotionally overwhelming, as astronauts live and work in small, enclosed environments with limited social interaction. The psychological strain that comes with such isolation can result in loneliness, anxiety, and mental health deterioration over time. This phenomenon, known as cabin fever, is exacerbated by the lack of natural environments and the routine activities that help maintain mental equilibrium on Earth. The monotony of life aboard a spacecraft or space station, coupled with limited personal space and privacy, amplifies feelings of frustration and irritability. To combat these effects, maintaining a structured daily schedule is crucial, along with engaging in routine physical exercise to help preserve both physical and mental health. The absence of immediate contact with family and friends further complicates the emotional strain. Although modern communication technologies like video calls and social media offer some relief, the long communication delays make it difficult to fully bridge the gap between spacefarers and their loved ones. The realization that returning to Earth is not possible for extended periods of time weighs heavily on the mind of any astronaut, intensifying feelings of homesickness and emotional distress. The mental challenges only deepen when astronauts find themselves in high-risk situations, knowing that help is far out of reach. To mitigate these psychological pressures, extensive training and resilience-building exercises are integral to astronaut preparation. Psychological support from Earth-based teams also plays a pivotal role in helping spacefarers maintain their mental health. Despite these preparations, the profound impact of isolation and stress remains a topic of ongoing research. As humanity ventures deeper into space, understanding how to safeguard the mental well-being of astronauts on extended missions will be crucial for the success of future space exploration. In parallel, the issue of space debris orbiting Earth is becoming an increasingly urgent concern. The growing number of defunct satellites, spent rocket stages, and debris from collisions is cluttering the space surrounding our planet, posing a serious threat to both existing and future missions. The task of managing this debris involves a combination of tracking, avoidance maneuvers, and innovative technological solutions. The first step in addressing the debris problem is tracking. Organizations like the United States Space Surveillance Network utilize a range of ground-based radar and optical telescopes to monitor and catalog more than 20,000 pieces of debris larger than a softball. This data is essential for predicting potential collisions and providing satellite operators with the necessary warnings. For smaller pieces of debris, which are harder to track but equally dangerous, simulations and statistical models help estimate their distribution and movement. When a potential collision is detected, satellite operators take evasive action by performing avoidance maneuvers. These maneuvers involve altering the satellite's trajectory using onboard thrusters to steer it clear of debris. However, these maneuvers come with their own set of challenges. They consume fuel, which in turn limits the satellite's operational lifespan, and must be carefully calculated to avoid creating new debris or collision risks. To combat this growing threat, space agencies are exploring innovative technologies to actively remove space debris. Concepts include robotic arms, nets, harpoons, and even lasers designed to either push debris into safer orbits or burn it up in Earth's atmosphere. The European Space Agency's ClearSpace One project and Japan's Aerospace Exploration Agency's Orbital Debris Removal project are leading the charge in developing these technologies. By combining tracking, avoidance, and active debris removal, we aim to mitigate the risks space debris poses to future missions and the safety of spacecraft. Meanwhile, in the realm of quantum physics, one of the most mind-boggling phenomena continues to intrigue scientists: quantum entanglement. This strange occurrence involves two particles becoming interconnected in such a way that the state of one instantly influences the state of the other, regardless of the vast distance between them. This seemingly instantaneous transfer of information defies the classical laws of physics, where information can only travel at the speed of light. When two particles become entangled, Their properties are interdependent. For example, if the spin of one entangled particle is measured and found to be up, the spin of the other particle will instantaneously be down, even if the two particles are light years apart. This creates what can be described as a quantum handshake across the universe, a remarkable phenomenon that challenges our fundamental understanding of time and space. Quantum entanglement continues to captivate researchers, like offering tantalizing possibilities for the future of communication, computing, and space exploration. In exploring these challenges, from the mental health of astronauts to the growing issue of space debris and the mind-bending mysteries of quantum physics, humanity stands at the precipice of monumental discoveries. The barriers are vast, but the pursuit of knowledge, safety, and survival in space pushes us ever forward towards a future where the impossible may one day become reality. Einstein was deeply puzzled by the phenomenon of quantum entanglement, famously calling it spooky action at a distance. This enigma has since become one of the cornerstones of modern physics, challenging our very understanding of reality. Researchers have worked tirelessly to test this phenomenon, conducting experiments over increasingly vast distances. One groundbreaking experiment involved entangled photons sent through optical fibers that spanned over 1,000 kilometers. Even at these staggering distances, the measurement of one photon's state immediately determined the state of its entangled twin. This confirmed that quantum entanglement was not just a theoretical concept, but something that could be observed on an enormous scale. Such results suggest that quantum mechanics operates in ways classical physics simply cannot explain. The implications of these findings are profound, revealing hidden layers of the universe that remain mysterious. While practical applications such as quantum communication and cryptography are still in development, the theoretical implications raise even more intriguing questions. How does the quantum realm transcend the limitations of space and time? What are the consequences for our understanding of information and its flow across vast distances? Quantum entanglement, even over cosmic distances, challenges the very fabric of space and time itself, hinting at a universe that is deeply interconnected in ways we are only beginning to comprehend. One of the most fascinating quantum phenomena is quantum tunneling, which plays a crucial role in stellar fusion, the process that powers stars, including our sun. Stellar fusion occurs when light atomic nuclei combine to form heavier nuclei, releasing enormous amounts of energy in the process. In the intense conditions of a star's core, hydrogen nuclei must overcome their natural electrostatic repulsion, known as the Coulomb barrier, before the strong nuclear force can bind them together. According to classical physics, overcoming this barrier would require prohibitively high amounts of kinetic energy. However, quantum mechanics offers an unexpected solution: quantum tunneling. Quantum tunneling allows particles to pass through energy barriers they should not, according to classical physics. Even when particles don't have enough energy to overcome a barrier directly, quantum mechanics permits a small but significant probability that they can tunnel through it. This is because particles at the quantum level exhibit wave-like properties, and these waves have a certain probability of being found on the other side of an energy barrier. In the dense, hot core of a star, where countless protons are in close proximity, quantum tunneling dramatically increases the likelihood of fusion events. Without quantum tunneling, stars would need to be much hotter, far beyond what is observed in the universe, for fusion to occur. This quantum effect is indispensable for sustaining the nuclear reactions that power stars and generate the energy that makes life possible on planets like Earth. In essence, quantum tunneling is what allows stars to shine, enabling them to sustain their energy output over billions of years, and thus ensuring the stability and longevity of the cosmic life cycle. Quantum effects also play a critical role in shaping the behavior of black holes, particularly near their event horizons. One of the most fascinating discoveries in this area comes from the work of physicist Stephen Hawking, who proposed the concept of Hawking radiation. This groundbreaking idea suggests that black holes are not entirely black, as classical physics would suggest. Instead, they emit radiation due to quantum effects near the event horizon. Hawking radiation arises from quantum fluctuations in what we once thought of as empty space. At the quantum level, space is anything but empty. It's teeming with virtual particle-antiparticle pairs that constantly form and annihilate each other. Near the event horizon of a black hole, the intense gravitational field can separate these pairs, with one particle falling into the black hole and the other escaping into space as radiation. This process causes the black hole to lose mass and energy over time, gradually evaporating it, a process that occurs extremely slowly for larger black holes but can be much more rapid for smaller ones. Another quantum paradox involving black holes is the information paradox. Classical general relativity asserts that any information swallowed by a black hole is lost forever. However, quantum mechanics posits that information cannot be destroyed, leading to a fundamental contradiction. To resolve this, scientists have explored various theories, such as holography, which suggests that all the information contained within a black hole could be encoded on its event horizon, like a hologram. This would preserve the information even as the black hole evolves and eventually disappears. Moreover, quantum mechanics could hold the key to understanding what actually happens inside a black hole. Theoretical work on quantum gravity, which seeks to unify general relativity and quantum mechanics, is crucial for gaining insights into the singularity at the heart of a black hole, where densities and gravitational forces increase infinitely. Several theories, such as string theory and loop quantum gravity, propose that the quantum nature of space-time may prevent singularities from existing, radically altering our understanding of black holes' internal structure and behavior. Through the concept of Hawking radiation, the potential resolution of the information paradox, and ongoing efforts to unify gravity and quantum mechanics, it's clear that black holes are far more complex and dynamic than we once thought. Lastly, the concept of quantum foam emerges from the intersection of quantum mechanics and general relativity, suggesting that space-time itself is not smooth and continuous at extremely small scales, specifically on the order of the Planck length, about 10 to the power of minus 35 meters. Instead, space-time is chaotic and frothy, with tiny fluctuations occurring at this minuscule scale. This idea challenges our classical understanding of space as a smooth backdrop and hints at a far more intricate and dynamic structure underpinning the fabric of the universe. These quantum effects, whether in black holes, stars, or the very nature of space-time, reveal a universe that is far more mysterious, interconnected, and strange than we can fully comprehend. The quest to understand these phenomena continues, promising to unlock profound insights into the deepest workings of reality itself. This notion was first proposed by physicist John Wheeler. In his framework, the fabric of the universe at the most minuscule scales is teeming with constant, transient fluctuations. These fluctuations are the direct result of the Heisenberg uncertainty principle, which states that certain pairs of physical properties, like energy and time, cannot be precisely determined at the same time. Consequently, at quantum scales, particles are created and annihilated incessantly, leading to a turbulent and dynamic environment. The implications of quantum foam are profound, reshaping our understanding of the very nature of spacetime. It challenges the classical notion of spacetime as a smooth, predictable continuum. Instead, it reveals a seething mass of energy fluctuations, where the fabric of the universe is constantly changing. These fluctuations may not just be theoretical anomalies, they could have real, observable effects. They may influence phenomena such as the propagation of light and the behavior of gravitational waves over vast cosmic distances. One theoretical consequence of quantum foam lies in its potential connection to quantum gravity, the elusive theory that seeks to reconcile the laws of general relativity with those of quantum mechanics. Several approaches, such as string theory and loop quantum gravity, have proposed different ways in which this foam-like structure could shape the universe. These theories suggest that space-time could be discretized at these tiny scales, or perhaps new dimensions could emerge. In this light, quantum foam becomes a frontier in modern physics, where a deeper understanding could unlock answers to some of the most profound questions regarding the nature of reality, the origins of the universe, and the unification of the fundamental forces. Quantum fluctuations in the early universe played a critical role in the formation of the cosmic structures we observe today. In the moments Following the Big Bang, the universe was in an extremely hot and dense state, where quantum mechanical effects ruled the landscape. These tiny quantum fluctuations in energy density occurred at subatomic scales, creating slight variations in the distribution of matter and energy. During the inflationary period, a rapid exponential expansion of the universe took place, occurring just fractions of a second after the Big Bang. These fluctuations, once infinitesimally small, were stretched to vast macroscopic scales as the universe expanded. The initially negligible variations in density grew larger and became imprinted onto the expanding cosmos. These density fluctuations acted as the seeds for the gravitational collapse that would eventually form galaxies, stars, and other cosmic structures. Regions with slightly higher density exerted a stronger gravitational pull, attracting more matter and growing over time. In contrast, areas with lower densities became voids, expanding as matter gravitated toward the denser regions. Remarkably, the cosmic microwave background, CMB, a faint glow left over from the early universe, offers a snapshot of these primordial fluctuations. Missions like COBE, WMAP, and Planck have captured this faint radiation, revealing a speckled pattern of temperature variations that directly map back to the density fluctuations from the inflationary era. These variations provide crucial evidence supporting the theory of inflation and offer a deeper understanding of the formation of structures in the universe. Thus, quantum fluctuations magnified by inflation laid the foundation for all cosmic structure. This remarkable bridge between the quantum world and the macroscopic universe showcases the profound interconnectedness of physical laws across different scales, leading to the diverse and complex cosmos we observe today. In extreme environments like neutron star collisions, quark-gluon plasmas, QGPs, form under conditions of intense temperature and density. During these high-energy events, the pressure and energy are so immense that protons and neutrons, the particles making up the nucleus of atoms, dismantle into their more fundamental components, quarks and gluons. Quarks are elementary particles, while gluons are the force carriers responsible for binding quarks together. When two neutron stars collide, their ultra-dense matter and immense gravitational forces generate unimaginable amounts of energy. The temperatures can soar to several trillion degrees, creating conditions that resemble the universe's first microseconds after the Big Bang. Under such extreme conditions, the usual structural boundaries that confine quarks within protons and neutrons dissolve. This breakdown results in the formation of a quark-gluon plasma, where quarks and gluons exist freely, unbound by larger particles. Detecting and studying QGP from these cosmic events typically relies on observing the aftermath of neutron star collisions. These events can be detected by gravitational wave detectors and telescopes capturing electromagnetic signals. Gravitational waves emitted during the collision provide valuable data about the star's masses and the dynamics of the merger. Subsequent electromagnetic signals, such as gamma-ray bursts and X-rays, can help confirm the creation of a quark-gluon plasma and the formation of new elements. The study of QGP and neutron star collisions not only deepens our understanding of these exotic objects, but also provides fundamental insights into the conditions of the early universe, shedding light on the extreme environments that existed in the universe's infancy. In particle colliders like the Large Hadron Collider, the laboratory creation of quark-gluon plasma, QGP, provides us with a controlled environment to study this fascinating state of matter. However, nothing compares to the extreme natural occurrences of QGP and neutron star collisions. These cataclysmic events offer unparalleled opportunities to explore physics under the universe's most extreme conditions, pushing the boundaries of our knowledge about matter and the fundamental forces that govern it. At the core of white dwarf stars, matter exists in an incredibly dense and intense state, creating what is known as degenerate matter. A white dwarf is the remnant of a star that has exhausted its nuclear fuel, expelling its outer layers and leaving behind a dense core composed primarily of carbon and oxygen atoms. The pressure in the heart of a white dwarf is so intense that electrons are squeezed into a highly compact arrangement. This immense pressure results from the star's gravity, which attempts to compress the matter further. However, unlike typical matter, the electrons in a white dwarf's core resist further compression due to a quantum mechanical principle called electron degeneracy pressure. This pressure arises from the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state simultaneously. Under these extreme conditions, the density of the white dwarf's core can become astonishingly high. In fact, a single cubic centimeter of white dwarf material could weigh several tons. The atoms themselves are stripped of their outer electrons, and the nuclei are packed closely together. Degenerate electrons form a kind of sea around them, and this electron degeneracy pressure is the force that prevents the white dwarf from collapsing under its own gravity. Over billions of years, the white dwarf will gradually cool and eventually become a black dwarf, a theoretical object that no longer emits significant heat or light. However, no black dwarfs are thought to exist yet due to the current age of the universe. The study of white dwarfs offers significant insights into stellar evolution, the behavior of matter under extreme conditions, and the fascinating interplay between quantum mechanics and gravitational forces. Cosmic strings, hypothetical one-dimensional defects believed to have formed in the early universe, could profoundly influence the large-scale structure of the cosmos. These strings are theorized to be incredibly thin, yet immensely dense, stretching across vast cosmic distances. They are thought to have emerged during phase transitions in the early universe, similar to cracks that form in ice as water freezes. Some grand unified theories, which attempt to unify all the fundamental forces of nature, predict the existence of cosmic strings. If these strings exist, their immense gravitational pull could significantly impact the formation and distribution of galaxies and galaxy clusters. As these strings move through space, their gravitational influence could cause matter to clump along their paths, potentially acting as seeds around which galaxies form. This process might explain certain large-scale patterns observed in the cosmic web, the vast network of galaxies and intergalactic matter. Additionally, cosmic strings might interact with the cosmic microwave background, CMB, the afterglow of the Big Bang, leaving behind distinct imprints. These strings, slicing through space-time, could cause minute but detectable disruptions or wake patterns in the CMB, observable as temperature anisotropies. Studying these patterns could offer indirect evidence of cosmic strings, providing crucial insights into the physics of the early universe. While no direct evidence for cosmic strings has been discovered yet, the concept continues to intrigue scientists. It offers a potential window into the universe's formative moments and underlying physics. Ongoing observations, such as those from the Planck satellite and future missions aimed at detecting subtle signals imprinted by cosmic strings, could open a new chapter in our understanding of the universe's complexity and origins. Strange quark stars, or simply strange stars, are hypothetical compact objects that are believed to consist of strange quark matter. This exotic state of matter is theorized to form under extreme pressure and density, where individual protons and neutrons break down into their constituent quarks, creating a dense soup of up, down, and strange quarks. Strange quark stars might form through the collapse of a neutron star, which is already an extraordinarily dense remnant of a massive star that has undergone a supernova explosion. In the interior of a neutron star, matter is squeezed to its most dense state without forming a black hole. If the central density becomes high enough, the neutrons themselves could decompose into their component quarks. In this scenario, strange quarks form alongside the up and down quarks, resulting in the creation of strange quark matter, a more stable state under such extreme conditions. One key difference between strange quark stars and regular neutron stars is their potential density and size. Strange quark matter is believed to be denser than the neutronium found in neutron stars. As a result, strange quark stars could have a smaller radius, but a much higher central density, making them an even more fascinating object of study in the realm of extreme astrophysics. In the vast expanse of the cosmos, the notion of strange quark stars brings a tantalizing mystery that could revolutionize our understanding of stellar evolution. These hypothetical stars, believed to be even denser than neutron stars, would possess extreme compactness, making them some of the most bizarre objects known to science. Detecting and confirming their existence, however, presents significant challenges. Though they might appear to share characteristics with neutron stars, such as emitting X-rays and possessing strong magnetic fields, there are subtle differences that could set them apart. For instance, their cooling rates might vary, or they might have slightly different mass-to-radius ratios. These slight discrepancies could offer astronomers the first clues that strange quark stars are real. In the coming years, advancements in both observational astronomy and high-density matter research, particularly through particle accelerators, may provide the breakthrough needed to confirm these exotic objects. The discovery of strange quark stars would add a vital piece to our understanding of how stars evolve and the extreme conditions under which matter behaves. Equally captivating are relativistic jets, which are among the most powerful phenomena in the universe. These jets emanate from the regions surrounding supermassive black holes at the centers of active galaxies. As material in the accretion disk, a swirling mass of gas and dust, spirals inward toward the black hole, it is subjected to intense gravitational forces, causing friction and heating the gas to extraordinary temperatures. Magnetic fields within the accretion disk, twisted and amplified by the disk's rotation, play a pivotal role in the formation of these jets. The Blandford-Zeneject process, a mechanism theorized to extract rotational energy from the black hole through magnetic interactions, is central to this process. As the material is ejected along the poles of the black hole, it accelerates to near light speeds powered by these magnetic forces. These jets extend across thousands of light years and are visible across a range of wavelengths from radio to gamma rays, allowing scientists to study their composition and the extreme physics at work near black holes. Through these observations, we deepen our understanding of black holes, accretion disks, and the behavior of matter in the presence of such powerful gravitational forces. Looking closer to home, our own sun, a medium-sized star, is not immune to the forces that govern stellar life cycles. Currently halfway through its life, the sun is in a stable phase known as the main sequence, where it fuses hydrogen into helium. However, in about 5 billion years, it will begin to run out of hydrogen, and its evolution will take a dramatic turn. The sun will enter the red giant phase, causing its core to contract and heat up, while its outer layers expand, potentially engulfing Mercury, Venus, and even Earth. The fate of Earth, though uncertain, may include being consumed by the expanding sun, or it could become a barren, lifeless rock as intense solar radiation strips away its atmosphere. After shedding its outer layers, the sun will leave behind a hot, dense core, a white dwarf, that will gradually cool over billions of years. The ejected material will form a planetary nebula, a stunning, glowing shell of gas and ionized particles, visible for vast distances. Meanwhile, the weakened gravitational influence of the sun will alter the orbits of the remaining planets. Outer giants like Jupiter and Saturn may drift outward, further disturbing the orbits of any remaining asteroids or comets. Over time, the once thriving solar system will become a quieter, more diffuse structure, with the remnants of the sun, now a faint white dwarf, serving as a quiet center. As we gaze into the vast timeline of the universe, the cosmic calendar offers a perspective that compresses the universe's history into a single year. This fascinating concept, introduced by astronomer Carl Sagan, helps us grasp the enormity of cosmic time. If we imagine the entire history of the universe as a single calendar year, the Big Bang occurs at midnight on January 1st, with the universe beginning its rapid expansion. By early March, the Milky Way galaxy begins to take shape. Our solar system forms around early September, and life on Earth emerges by late September. Complex life evolves by mid-December, and the dinosaurs dominate Earth just a few days before the end of the year, only to vanish on December 26th due to a catastrophic asteroid impact. Humans, meanwhile, arrive just before midnight on December 31st. The span of recorded human history is so brief, merely the last few seconds of the year, underscoring how young our civilization is in the grand scheme of the universe. Looking ahead, the universe will continue to evolve long after humanity's time has passed. In several billion years, the Milky Way is expected to collide with the Andromeda Galaxy, forming a new, larger galaxy. As the sun enters its red giant phase, it will alter the dynamics of the solar system. Eventually, the death of the sun will be followed by the gradual decline of star formation as the universe's gas supply diminishes. As the universe continues to expand, galaxies will become increasingly isolated, with dark energy pushing them further apart. In the distant future, the universe may approach a state known as heat death, where entropy reaches its maximum and all thermodynamic processes cease. This will leave a dark, cold cosmos populated only by the remnants of once glorious stars and galaxies. The cosmic calendar not only reminds us of the fleeting nature of human history in comparison to the grand expanse of cosmic time, but it also offers a glimpse into the profound future of the universe, a future that extends far beyond the reach of human imagination. The evolution of galaxies is a captivating journey, stretching across cosmic time where every interaction, merge, and internal process plays a pivotal role in shaping the grand structures we observe today. This is a tale of cosmic evolution, written in the stars and galaxies, unfolding ever since the Big Bang. In the earliest days of the universe, shortly after the Big Bang, it was a hot, dense soup of primordial gases, mainly hydrogen and helium. As the universe expanded and began to cool, gravity took hold, slowly pulling these gases together. This led to the formation of the first cosmic structures, known as proto-galaxies, which marked the beginning of galaxy formation. These early galaxies were small, irregular, and frequently disrupted by mergers and interactions. Such chaotic conditions were common as proto-galaxies collided, merging into larger and more complex structures. This hierarchical model of galaxy formation reveals that over time, today's massive galaxies, like our very own Milky Way, formed from the amalgamation of countless smaller ones. It's a process that hints at a deep cosmic truth. Galaxies are not static, but dynamic and constantly evolving. Star formation central to this evolution played a massive role in shaping early galaxies. In the early universe, the rate of star formation was high, leading to the formation of bright, blue galaxies filled with young, hot stars. Over billions of years, however, galaxies exhausted their gas reserves, and the pace of new star formation slowed down. As a result, galaxies began to appear redder, hosting older, cooler stars. Spiral galaxies like the Milky Way maintained their star-forming regions, with their spiral arms acting as the birthplaces of new stars, continuing to evolve and shape their structure. However, galaxy evolution doesn't happen in isolation. Galaxy interactions, particularly mergers and tidal forces, have a profound influence on the cosmic dance of galaxies. When galaxies collide, their mutual gravitational forces can spark bursts of star formation, creating spectacular structures, from elliptical to lenticular galaxies. These interactions can also lead to the formation of supermassive black holes at the centers of galaxies, which in turn influence star formation and contribute to the overall stability of the galaxy. These black holes are not just passive observers, they shape their host galaxies in ways that we are only beginning to fully understand. The diversity of galaxies we see today, from magnificent spirals to massive elliptical galaxies and even irregular ones, exists because of these ongoing processes of star formation, mergers, and interactions. Observations through powerful telescopes like Hubble and upcoming missions such as the James Webb Space Telescope continue to enrich our understanding. They allow us to look back through billions of years of cosmic history, helping us piece together the incredible story of how galaxies, including our own, have evolved. Yet, the story of the universe is far from over. What lies ahead for our universe? The ultimate fate of everything we know hinges on the rate of expansion and the mysterious force known as dark energy, which is driving the universe's accelerating expansion. While predicting the precise future remains a challenge, several theories offer fascinating possibilities. One prevailing scenario is the Big Freeze, or heat death. In this theory, dark energy continues to push galaxies further apart at an ever-accelerating pace. Over time, stars exhaust their nuclear fuel and cease forming new ones. Galaxies fade into darkness, leaving behind remnants like white dwarfs, neutron stars, and black holes. Trillions of years from now, the universe will become increasingly sparse, its energy uniformly cold, and thermodynamic processes will cease. Another theory is the Big Rip, where dark energy grows stronger over time. This increase in repulsive force could eventually overpower all gravitational bonds, leading to a cataclysmic end. As the universe expands, galaxies, stars, planets, and even atomic particles would be torn apart in a dramatic cosmic event, literally ripping the universe apart. Finally, there's the Big Crunch, a cyclical model that suggests the universe's expansion could eventually slow down and reverse. If dark energy weakens, gravity would reignite, causing the universe to collapse. All matter and energy would be drawn back into a hot, dense state similar to the conditions of the Big Bang. This model proposes the possibility of a cosmic rebirth, where the universe, after a dramatic collapse, could emerge anew from the ashes. No matter which scenario unfolds, the evolution of galaxies is a story of constant change, driven by the forces of gravity, dark energy, and cosmic interactions. This grand narrative, unfolding over billions of years, will continue to shape the universe and its galaxies for eons to come. The Big Bounce hypothesis offers a captivating possibility. The universe may not have one definitive beginning or end. Instead, it could experience an endless cycle of expansion and contraction. After each potential Big Crunch, where everything collapses back into a singularity, conditions might reset the universe, sparking another Big Bang. This eternal cycle of creation, destruction, and rebirth paints a mesmerizing picture of our universe's future, one that challenges the conventional beginning and end narrative. These concepts highlight the limitations of our current understanding of the universe's ultimate destiny. Despite our advancements, we remain on the edge of unlocking the mysteries surrounding dark energy and the structure of the universe at its grandest scale. Ongoing observations and studies, especially focused on these areas, are vital. They could one day give us clearer insights into these theories and possibly reveal the true fate awaiting our cosmos. Are we merely part of a cycle, or is the universe heading towards an entirely different fate? As astronomers refine their observations, they edge closer to answering these profound questions. Turning to the evolution of galaxies, we know that stellar populations shift dramatically over billions of years, dictated by forces like star formation, stellar evolution, and interactions between galaxies. A young galaxy, teeming with life, is often dominated by population 3 stars. These stars are the first of their kind, composed mostly of hydrogen and helium. They burn hot and bright but live fast, dying in dramatic supernovae that enrich the surrounding space with heavier elements. This cycle of birth and death paves the way for the formation of the next generation of stars, population 2 stars. Population 2 stars, older and containing fewer heavy elements than their younger counterparts, are typically found in the galactic halo and globular clusters. As these stars age, many will transform into red giants, shedding their outer layers to leave behind white dwarfs. Larger stars will explode in supernovae, continuing the cycle of enriching the galaxy. Over time, population I stars, those rich in heavier elements, begin to form. These stars dominate the spiral arms of galaxies where gas and dust are abundant, and star formation continues, though at a declining rate as the galaxy grows older. As galaxies mature, star formation becomes increasingly sluggish due to the depletion of available gas. Yet, galactic mergers and interactions can spark a rebirth. When galaxies collide, their gas clouds compress, triggering bursts of new star formation. These cosmic collisions also alter the structure and dynamics of the galaxies, mixing populations of stars and changing their trajectory. Eventually, though, as the galaxy ages and its resources diminish, the once bright blue hues of young stars fade, leaving a more subdued, reddish glow of older, cooler stars. This slow, inevitable shift marks the passage of time in the cosmic landscape. Shifting from cosmic evolution to the extraordinary challenges of interstellar travel, one might wonder what it would take to build and power spacecraft that could journey across the vast distances of our universe. The task is daunting, but innovative propulsion systems could make this ambitious leap possible. One promising method involves solar or laser sails, thin, reflective sails that harness the momentum of light. Solar sails use sunlight to propel the spacecraft forward, while laser sails rely on powerful lasers to push the craft at incredible speeds. Projects like Breakthrough Starshot are exploring these technologies with the goal of sending small, lightweight probes to nearby star systems at up to 20% of the speed of light. These sails would need to be incredibly durable to withstand the harsh conditions of space, including radiation and particle bombardment. But even with such advancements, the distances involved in interstellar travel remain vast, requiring years, decades, or even centuries for a spacecraft to reach its destination. Another possibility for interstellar propulsion lies in fusion rockets. These engines would harness the power of nuclear fusion, the same process that powers the stars. By fusing isotopes like deuterium and tritium, a fusion rocket could achieve higher efficiencies than conventional chemical rockets, making long-duration missions feasible. While the technology still faces significant hurdles, such as managing the intense heat and energy produced by fusion reactions, the potential for high-efficiency propulsion is undeniable. Finally, antimatter engines, though still very much in the realm of science fiction, represent the pinnacle of futuristic propulsion. The collision of matter and antimatter releases staggering amounts of energy, potentially propelling spacecraft at significant fractions of the speed of light. The challenges, however, are immense. Producing, storing, and controlling antimatter is a monumental task that humanity has yet to conquer. For energy production, solar panels remain a reliable option within our solar system, though their efficiency diminishes as a spacecraft ventures farther from the sun. In the cold void of interstellar space, alternative energy sources will be crucial to sustaining long-duration missions. In all, while we are just beginning to scratch the surface of understanding the universe's fate and the technology needed for interstellar exploration, the road ahead is filled with promise. The mysteries of both our cosmos and the technologies required to venture beyond it are still unfolding. In the quest to conquer the vastness of space, nuclear power sources like radioisotope thermoelectric generators and compact nuclear reactors are indispensable. These power systems provide a consistent and long-lasting energy supply essential for running spacecraft systems and instruments, especially during deep space missions where solar power is no longer an option. At the same time, advances in energy harvesting are beginning to expand our capabilities. Concepts such as tapping into cosmic background radiation and utilizing onboard batteries designed for deep space environments hold great promise. These innovations, while still in their early stages, sketch a compelling roadmap for humanity's aspirations of interstellar exploration. However, realizing this dream will require not only technological breakthroughs, but a deeper understanding of how to interact with and survive in the hostile interstellar medium. Spacecraft exploring distant stars require not only power, but the capacity to support life for extended missions. The concept of constructing large-scale space habitats presents one of the most challenging yet potentially transformative endeavors in space exploration. These habitats, which could orbit Earth, the Moon, or even Mars, aim to provide a sustainable living environment for long-term space missions or permanent human habitation. One of the primary hurdles lies in creating life support systems that sustain air, water, food, and waste management. These systems must operate in a closed loop, recycling air, water, and nutrients to keep human life viable. Technologies for water purification, atmospheric control, and food production, such as hydroponics or aeroponics, are essential. But keeping these systems running without regular resupply from Earth is a daunting challenge. Beyond life support, the structural integrity and safe space habitats are paramount. Habitats must withstand the dangers of micrometeoroid impacts and the extreme conditions of space, including temperature fluctuations and the vacuum of space. Moreover, radiation from cosmic rays and solar particles poses a significant risk to human health. Effective shielding made from materials like regolith, water, or specialized alloys is a critical component of habitat design. Some even propose using magnetic fields to deflect harmful radiation, though this remains a concept that requires further research. Logistics also present considerable difficulties. Constructing these habitats would require multiple space launches, advanced robotics, and the potential use of in-situ resource utilization, ISRU, to source materials from celestial bodies like the Moon or asteroids. Technologies such as 3D printing are being explored to build habitats from local materials, reducing the need to transport bulky items from Earth. Coordinating these missions will require highly reliable spacecraft and precise planning to ensure success. Equally important are the human factors involved in long-term space habitation. The psychology and social dynamics of living in isolated, confined environments must be carefully considered. Creating habitats that promote mental and emotional well-being will be crucial for the success of long-duration missions. Research from the International Space Station and analog missions on Earth provides valuable insights into these aspects, helping to mitigate the psychological challenges faced by astronauts. As we continue to refine our understanding of life in space, these findings will guide the design of habitats that not only support human life, but also foster a sense of community and well-being. Together, the integration of sustainable life support, structural resilience, logistical feasibility, and psychological health will form the foundation for large-scale space habitats, an achievable goal that brings humanity one step closer to living beyond our home planet. Meanwhile, in the realm of interstellar exploration, laser propulsion stands as one of the most promising concepts. Imagine spacecraft that could travel to nearby star systems in a fraction of the time it would take with conventional propulsion methods. The principle behind laser propulsion involves using intense laser beams to propel lightweight spacecraft equipped with highly reflective sails. These sails, often made from materials such as graphene or ultra-thin polyamide, reflect photons from powerful ground or space-based lasers. Each photon carries a tiny amount of momentum, but over time, the continuous bombardment of photons delivers a significant amount of thrust. This process gradually accelerates the spacecraft to a substantial fraction of the speed of light, potentially allowing probes to reach distant stars within a human lifetime. One of the most ambitious projects based on this idea is Breakthrough Starshot. The initiative aims to launch small, lightweight probes weighing only a few grams, equipped with a light sail a few meters in size. High-powered lasers on Earth would focus their beams onto the sail, providing the necessary thrust to accelerate the probe to speeds of up to 20% of the speed of light. At this speed, a probe could reach a star system like Alpha Centauri in just over 20 years, an astonishing breakthrough in space travel. However, to realize this vision, several technical challenges must be overcome. The first challenge lies in the development of extremely powerful and precise laser systems that can project coherent, high-intensity beams over vast distances. These lasers must operate reliably for extended periods to provide consistent acceleration. Engineers are currently exploring phased laser arrays, which combine the power of multiple lasers and direct it precisely onto the sail. The second challenge involves the creation of ultra-lightweight sails capable of withstanding the immense energy from the laser beams. These sails must be highly reflective and resistant to heat in order to survive the intense radiation pressure. The materials chosen for these sails must also be incredibly durable, as they will need to endure extreme conditions in space, including cosmic radiation and micrometeoroid impacts. These innovations, while still in development, may one day revolutionize our approach to interstellar travel. Thus, while the dream of sending probes to distant star systems remains a long-term goal, the technologies that could make it a reality are progressing rapidly. With each breakthrough, humanity inches closer to mastering the art of interstellar exploration. The future of interstellar exploration hinges on overcoming extraordinary challenges. Accurate targeting and navigation are at the core of this pursuit. Even the slightest deviation in the initial laser targeting or minor flight imprecisions could lead to catastrophic errors in trajectory over the vast, unforgiving distances of interstellar space. This means that advanced guidance systems are not just useful, but absolutely essential. And that's not all. Onboard course correction capabilities will be crucial, ensuring that these fast-moving probes stay on course as they venture further than humanity has ever dared to imagine. However, the obstacles don't end with reaching distant destinations. Once the probes are in flight, communication becomes an even greater challenge. With such immense distances between Earth and these probes, the speed at which they travel only compounds the problem. Despite their small size, these spacecraft need sophisticated instruments capable of gathering invaluable data and transmitting it back across the vast void of space. This requires innovations in miniaturized electronics and the development of high-gain antennas, technologies that enable data transmission across light years. Overcoming these challenges is key to unlocking the next great frontier of human exploration, interstellar travel. If these hurdles can be navigated, humanity will stand at the threshold of a new era, where the mysteries of neighboring stars and their exoplanets could be uncovered. Laser propulsion could become the driving force of this bold journey, advancing us beyond the confines of our solar system and potentially making interstellar travel a reality. But there's another crucial milestone along the way: directly detecting Earth-like exoplanets. This too comes with its own set of challenges. These exoplanets are often small, faint, and hidden behind the glare of much brighter stars. The good news is that technology is rapidly advancing, and we are on the cusp of breakthroughs that could change everything. One of the most promising avenues involves space-based telescopes equipped with coronagraphs or starshades. These specialized instruments are designed to block out the intense light of a star, creating a shadow that allows us to observe the faint light emitted by planets orbiting those stars. Starshades, large flower-shaped structures positioned in space, can effectively block the star's light while letting the telescope capture the distant planet's dim glow. Instruments like the upcoming James Webb Space Telescope, along with proposed missions like the Habitable Exoplanet Observatory, are incorporating these technologies to make direct exoplanet observation a reality. Another exciting technique is optical interferometry, a method that combines light from multiple telescopes to simulate a much larger telescope. This enhances the resolution, allowing us to distinguish between the light from a star and the faint glow of its surrounding planets. Missions such as the proposed Terrestrial Planet Finder and the Infrared Space Interferometer aim to use this cutting-edge approach to directly image and analyze Earth-like exoplanets. For those looking closer to home, adaptive optics play a pivotal role for ground-based telescopes. By compensating for the blurring effects of Earth's atmosphere, these systems allow telescopes to achieve near-theoretical resolution, making it possible to detect exoplanets with unprecedented clarity. Large ground-based telescopes like the Extremely Large Telescope and the Giant Magellan Telescope will leverage these systems to significantly enhance their capabilities in the search for habitable worlds. Through innovation, persistence, and breakthroughs in technology, humanity is inching closer to the possibility of interstellar exploration. What once seemed like the realm of science fiction is now on the cusp of becoming reality. The dream of reaching neighboring stars, discovering new worlds, and perhaps even encountering Earth-like exoplanets is within our grasp. Advancements in spectrograph technology have revolutionized our ability to study exoplanets, opening new avenues for understanding the nature of distant worlds. High-precision spectrographs, which analyze the light reflected or emitted by exoplanets, are now capable of detecting specific chemical signatures and atmospheric compositions. Instruments like the ACell spectrograph, designed for rocky exoplanets, and stable spectroscopic observation systems are leading the charge in this field. These tools can identify vital biomarkers such as oxygen, methane, and water vapor in the atmospheres of exoplanets, marking a significant leap forward in our ability to study planetary habitability. By combining these advanced technologies, astronomers are now capable of moving beyond merely detecting Earth-like exoplanets to delving deeper into the study of their atmospheres and their potential to support life. These tools not only provide a clearer view of distant worlds, but also help us understand how common or rare such Earth-like environments might be in the vastness of space. The ability to study these exoplanetary atmospheres opens up a fascinating question. Are we alone in the universe, or do other worlds like ours exist, waiting to be discovered? Another remarkable advancement in space exploration is the technique of gravitational assists, also known as gravity slingshots. This method, a time-tested technique used to enhance the efficiency of space missions, is particularly invaluable when exploring the outer solar system. By using the gravitational field of a planet or another celestial body, spacecraft can gain speed without relying on additional onboard propulsion. When a spacecraft approaches a planet, it falls into the planet's gravitational well, accelerating as it swings around the planet. By the time it exits, it leaves with an increased velocity relative to the Sun, having borrowed some of the planet's momentum. One of the most famous uses of gravitational assists occurred during the Voyager missions. Voyager 1 and Voyager 2 achieved remarkable feats, visiting multiple outer planets by carefully navigating gravitational assists. Voyager 2, for example, executed a series of precise slingshots to visit Jupiter, Saturn, Uranus, and Neptune. These assists boosted the spacecraft's speed and altered its trajectory, allowing it to reach distant planets with reduced fuel consumption. Today, new missions can also utilize this technique by planning multi-assist trajectories, conserving fuel and reducing travel time. Spacecraft might first use a flyby of Venus or Earth to gain speed before heading out to the outer planets, or take advantage of Jupiter's massive gravitational field to propel themselves toward destinations like Saturn, Uranus, Neptune, or even the Kuiper Belt and beyond. The efficiency of gravitational assists is also exemplified by NASA's Juno spacecraft, which used a flyby of Earth to reach Jupiter, increasing its speed by over 13,000 kilometers per hour. More advanced techniques, such as interplanetary pogo sticking, involve using smaller planetary assists to build up speed gradually. This method optimizes trajectories and reduces the need for heavy propulsion systems, making deep space exploration more cost-effective and feasible. With the use of advanced mission planning software and real-time trajectory adjustments, space missions can now execute these assists with unprecedented precision, unlocking new frontiers in space science and exploration. The potential entry of a rogue planet into our solar system would be an extraordinary event with profound implications. Rogue planets, which are not bound to any star system and drift aimlessly through the galaxy, could pose significant challenges if they ventured close to or even entered our solar system. Their gravitational influence could disrupt the outer regions of the solar system, causing perturbations in the orbits of distant objects like those in the Kuiper Belt and the scattered disk. This disruption could redirect these objects toward the inner solar system, increasing cometary activity and the rate of meteor impacts on planets, including Earth. As a rogue planet moves closer, its gravitational pull could also have dramatic effects on the gas giants in the outer solar system. A close encounter with Jupiter or Saturn could destabilize their moons, altering their orbits, or even flinging some moons out of orbit entirely. The planet's gravity might also capture new moons, further complicating the dynamics of these already complex systems. In the worst-case scenario, a rogue planet's trajectory could destabilize the entire solar system, throwing our carefully balanced planetary system into chaos. The cosmic ballet of gravitational mechanics continues to surprise us, and the study of such phenomena offers a glimpse into the extraordinary forces that govern the universe. Through these advancements in technology and an ever-deepening understanding of the cosmos, we inch closer to answering some of humanity's oldest questions about the nature of space, the possibility of life beyond Earth, and the fate of our solar system. If a rogue planet were to have a close encounter with Earth or Mars, the gravitational forces at play could trigger severe orbital disruptions. Even without a direct collision, the rogue planet could still alter Earth's orbit, shifting it closer or farther from the Sun. Such a shift could bring about drastic climate changes that would reshape life on Earth. The tidal effects alone could significantly amplify geological activity, such as earthquakes and volcanic eruptions, shaking the planet to its core. Additionally, any alterations to Earth's rotation or axial tilt could drastically disrupt the seasons and weather patterns, creating unpredictable and potentially catastrophic environmental consequences. However, if this rogue planet were to settle into a stable orbit within our solar system, it might eventually integrate itself without causing catastrophic disruptions. Its passage might leave lasting changes, but with time, the gravitational disturbances would likely stabilize. On the other hand, if the rogue planet were to pass through the solar system without becoming permanently integrated, the initial disturbances would gradually fade, but not without leaving an indelible mark on the solar system's structure and dynamic evolution. In either case, the importance of tracking and predicting such an event becomes clear. By understanding the rogue planet's characteristics and trajectory, astronomers could model its potential impacts, helping humanity prepare for and mitigate the risks posed by this celestial intruder. Though the entrance of a rogue planet into our solar system is an unlikely event, it underscores the importance of continued observation and advancements in our understanding of cosmic phenomena. Our ability to detect and predict such astronomical anomalies could determine our capacity to protect both human life and the stability of the solar system. As the world of celestial mechanics continues to evolve, we must remain vigilant to the potential threats lurking in the vastness of space. Meanwhile, potentially hazardous asteroids, PHAs, are a more frequent, though still rare, concern for Earth. These are asteroids that pass within about 7.5 million kilometers of our planet and are large enough to cause significant regional damage if they collide with Earth. While the frequency of these close encounters varies depending on the size and orbit of the asteroids, smaller objects, ranging from a few meters to tens of meters, pass close to Earth more often. These smaller asteroids, though numerous, typically burn up in the atmosphere and pose little threat to the surface. However, their frequent passages remind us of the potential hazards that space holds. Medium-sized PHAs, typically several hundred meters in diameter, pass close to Earth less frequently, but still regularly, sometimes once every few years or decades. The consequences of an impact from one of these objects could be severe, causing regional devastation similar to the 1908 Tunguska event, which leveled over 2,000 square kilometers of forest in Siberia. While these objects are a threat to Earth, they are still relatively small compared to the truly dangerous asteroids that could cause global consequences. Large PHAs, those over 1 kilometer in diameter, are much rarer. These massive space rocks pass by Earth on timescales of centuries, but when they do, they pose a significant threat. Their size and energy have the potential to cause catastrophic global consequences, affecting Earth's climate and potentially leading to mass extinctions. The impact that contributed to the extinction of the dinosaurs, which occurred around 66 million years ago, serves as a stark reminder of the destructive power such asteroids possess. NASA and other space agencies actively track PHAs through programs such as the Near-Earth Object Observations, NEO-O. These initiatives rely on telescopes and radar systems to monitor and characterize the orbits of near-Earth objects, enabling astronomers to predict potential threats years in advance. Although there are no known asteroids on a collision course with Earth in the foreseeable future, continuous monitoring remains essential. With advances in telescope technology, data collection, and computational modeling, our ability to detect and predict the trajectories of these space rocks has improved significantly. This ongoing vigilance is critical for planetary defense, allowing scientists to develop potential mitigation strategies, such as deflection missions or even evacuation plans, in case a credible threat is identified. Another potentially devastating event is the occurrence of a nearby gamma-ray burst, GRB. These bursts are intense, extremely energetic explosions believed to result from cosmic events like the collapse of massive stars into black holes or neutron star mergers. While these bursts typically originate in distant galaxies, if one were to occur relatively close to our solar system, its effects could be catastrophic. One of the primary dangers of a nearby GRB is the intense gamma radiation it emits. If Earth were to be in the direct line of this radiation, the outer layers of our atmosphere would absorb a significant amount of energy, triggering a cascade of chemical reactions. The most notable consequence of this burst of radiation would be the breakdown of nitrogen and oxygen molecules, leading to the formation of nitrogen oxides. These compounds would severely deplete the ozone layer, the protective barrier that shields life on Earth from harmful ultraviolet radiation. Even partial destruction of the ozone layer could have disastrous effects, increasing UVB radiation levels at the surface. The resulting rise in skin cancer, cataracts, and other health issues could be catastrophic for humanity. Additionally, ecosystems, particularly marine life, would suffer, as phytoplankton, a crucial part of the ocean food chain, would be unable to survive in the higher levels of UV radiation. The presence of nitrogen oxides could also contribute to the formation of smog and acid rain, further damaging Earth's fragile ecosystems. The delicate balance of life, both on land and in the oceans, would be severely impacted by the long-term effects of such an event. A nearby GRB could disrupt the planet's very foundation, altering not just life, but the conditions that support it. In conclusion, while the likelihood of encountering a rogue planet, asteroid, or gamma-ray burst remains small, the potential impacts of such events are profound, and understanding them is critical to the future of life on Earth. Additionally, increased ultraviolet radiation could drastically alter atmospheric dynamics and weather patterns. While the atmosphere would absorb most of the direct gamma rays from these cosmic events, secondary radiation could still reach the surface. The effects of this radiation may include radiation sickness, depending on the proximity and duration of the gamma ray bursts, GRBs. As we look back at Earth's history, there is evidence suggesting that mass extinction events could have been triggered by similar cosmic occurrences. A sufficiently close and intense GRB could lead to a biological crisis, drastically affecting biodiversity and possibly causing a mass extinction event. Fortunately, such events within the Milky Way galaxy are exceedingly rare. Current astrophysical research indicates that a deadly GRB striking Earth is an extremely rare event, with estimates suggesting it might only occur once every few 100 million years. However, to manage such risks, ongoing astronomical observations and studies are crucial. They help improve our understanding of GRBs, including their origins, frequency, and potential threats to Earth. This vital knowledge aids in preparing for and mitigating the impacts of these cosmic hazards, ensuring that we remain vigilant in protecting life on our planet from these extreme, albeit rare, extraterrestrial events. The role of planetary impacts in the evolution of solar systems cannot be overstated. These cataclysmic events, ranging from the collision of small meteoroids to massive planetary scale impacts, are responsible for driving dynamic processes that significantly alter celestial bodies and their environments. During the early stages of solar system formation, impacts were both frequent and transformative. This period, known as the heavy bombardment, saw protoplanets and planetesimals colliding as they coalesced from the protoplanetary disk of gas and dust. These high-energy impacts contributed to the accretion of planetary bodies, ultimately forming larger planets from smaller building blocks. Through these collisions, planets grew in mass and differentiated into distinct layers, including cores, mantles, and crusts. A striking example of these impacts is the formation of the Moon. The leading theory, known as the giant impact hypothesis, suggests that the Moon formed as a result of a colossal collision between the early Earth and a Mars-sized body named Theia. The debris from this impact eventually coalesced to form the Moon. This event not only shaped the Earth-Moon system, but also had lasting effects on Earth's axial tilt and rotation, influencing the planet's climate and the stability of its seasons. Throughout history, planetary impacts have periodically reset Earth's biological clock. One of the most significant events in Earth's history was the Chicxulub impact, linked to the mass extinction that wiped out the dinosaurs around 66 million years ago. These impacts can trigger drastic climate changes, volcanic activity, and the emergence of new evolutionary pathways by creating unique niches and eliminating dominant species. Furthermore, planetary impacts played an essential role in delivering volatiles and organic molecules to Earth. The theory of panspermia suggests that these impacts could have transported microbial life and organic molecules between planets, potentially seeding life on Earth. During the early bombardment phase, impacts likely delivered large amounts of water and organic compounds to Earth and other terrestrial planets, contributing to the conditions necessary for life to arise. Even in modern times, smaller-scale impacts continue to shape planetary surfaces, creating craters, altering landscapes, and impacting atmospheric conditions. Studying impact craters on celestial bodies like the Moon, Mars, and Mercury provides valuable insights into the history and evolution of our solar system. These planetary impacts are a fundamental force in sculpting the architecture and development of solar systems. They drive the formation of planetary bodies, create moons, influence geological and atmospheric conditions, and may even play a role in the origin and distribution of life itself. Understanding the processes that govern planetary impacts helps us piece together the complex history of our solar system and offers crucial clues about the evolution of other planetary systems throughout the universe. By continuing to study these phenomena, we expand our understanding of the forces that shape our planet and the cosmos. In a distant future, a monumental event will unfold, shaping the very fabric of our universe, the collision between the Milky Way and the Andromeda Galaxy. Expected to occur in approximately 4 billion years, this cosmic collision is already in motion, Andromeda and the Milky Way are hurtling toward each other at speeds reaching around 110 kilometers per second. While this sounds catastrophic, the actual consequences for our solar system and others within these galaxies are far more complex and fascinating than one might think. As Andromeda draws closer, one of the first noticeable effects will be a dramatic shift in the night sky. Over millions of years, Andromeda will appear larger and more prominent, slowly taking center stage in our celestial view. This changing sky will be a visual spectacle, a precursor to the forces at play in the galaxy's collision. When the galaxies finally meet, the gravitational pull between them will initiate the cosmic merger. However, because galaxies are vast and primarily made up of empty space, direct collisions between stars are extraordinarily rare. Instead, it's the gravitational interactions between stars and planetary systems that will take center stage. These forces will lead to fascinating phenomena, such as the compression of interstellar gas and dust, which will spark intense star formation known as starbursts. New stars, possibly accompanied by planetary systems, will shine brightly as cosmic nurseries. While direct stellar collisions are rare, the gravitational interactions will alter the orbits of stars and planetary systems, pushing some systems into intergalactic space to become rogue stars. Others may be pulled into new orbits around the merged galaxy's core or relocated to entirely different regions within the galaxy. Both the Milky Way and Andromeda host supermassive black holes at their centers. As the galaxies draw nearer, these black holes will eventually spiral towards each other, eventually merging into one, releasing a tremendous burst of energy in the form of gravitational waves. This final phase of the collision will be one of the most spectacular, as the two galaxies merge into a single larger elliptical galaxy, often referred to as Milkomeda or Mildroma. This new galaxy will be a stark contrast to the separate Milky Way and Andromeda, with a different structure and star formation rate. Over billions of years, the merged galaxy will settle and stabilize into a new cosmic configuration. As for our solar system, the immediate effects of the collision might be relatively minimal. While the night sky will undergo dramatic changes with a more crowded and dynamic vista, the likelihood of our solar system being ejected or drastically disturbed is low. However, gravitational forces may shift our position within the galaxy, possibly drawing our solar system closer to or further from the galactic core. The collision between the Milky Way and Andromeda represents both a destructive and creative force, reshaping our local universe in ways we can hardly imagine. It is a vivid reminder of the ever-evolving nature of the cosmos, where catastrophic events lead to the birth of new stars and the reshaping of galactic structures. On a smaller but equally fascinating scale, the discovery of Oumuamua, an interstellar object that passed through our solar system in October 2017, offers scientists a unique glimpse into the mysteries of interstellar space. This cigar-shaped object, named after the Hawaiian word for scout or messenger, is the first known visitor from another star system, providing a rare opportunity to study an ancient relic from beyond our solar system. Its unusual properties and origin continue to intrigue researchers, adding to the growing catalog of cosmic wonders waiting to be uncovered. Through these cosmic events, whether the grand merging of galaxies or the curious passage of an interstellar visitor, our understanding of the universe expands, unveiling the dynamic and often mysterious forces that drive the evolution of the cosmos. In the vast expanse of our universe, certain phenomena challenge our understanding, and Oumuamua stands as one of the most captivating. This interstellar visitor, which entered our solar system in 2017, displayed several remarkable characteristics that set it apart from typical asteroids and comets. First, its velocity and trajectory indicated that Oumuamua was not a native resident of our solar system, but rather a traveler from the depths of interstellar space. Unlike objects that are gravitationally bound to our sun, Oumuamua's hyperbolic orbit suggested it was simply passing through, unlikely to return, a fleeting visitor from a distant star system. Perhaps the most striking feature of Oumuamua was its unusual shape. Observations revealed that it was elongated, with a length-to-width ratio of approximately 10:1, resembling a cigar or a flattened pancake. This starkly contrasts with most comets and asteroids, which tend to be more irregular or spherical in shape. Its estimated dimensions were equally extraordinary, measuring roughly 800 meters in length and just 80 meters in thickness. The composition and behavior of Oumuamua raised even more questions. Initially thought to be a comet due to its interstellar origins, it lacked the typical features of a comet, such as a visible tail or coma. Rather than sublimating as it neared the sun, Oumuamua exhibited strange non-gravitational acceleration hinting at the possibility of outgassing. However, the absence of visible gases left scientists speculating about the nature of this acceleration, suggesting that the object might be emitting volatile substances that were difficult to detect with existing technology. As scientists scrambled to make sense of Oumuamua's strange behavior, several hypotheses emerged. One theory proposed that it could be a fragment of a larger body, possibly ejected from its home system after a cosmic collision. Some researchers speculated that it might be composed of a material that behaved differently under solar heating. Others suggested that Oumuamua could be an icy body with an organic-rich crust, which prevented visible sublimation. More boldly, a few scientists, including those from Harvard University, floated the idea that Oumuamua might be an artificial object, possibly a light sail or probe sent by an advanced extraterrestrial civilization. However, the majority of the scientific community deemed this hypothesis unlikely, calling for more data and further observation to clarify the object's true nature. The brief visibility of Oumuamua meant that scientists had limited time to observe it and understand its characteristics. This limitation underscored the importance of fast response times and efficient observational strategies when studying such rare and transient interstellar visitors. In the wake of Oumuamua's passage, telescopes and space observatories around the world began scanning the skies for other objects of a similar nature, hoping that more discoveries could shed light on the processes that govern the universe beyond our solar system. Beyond the mysteries of interstellar objects, the scientific community has also been grappling with the lithium problem. This refers to the discrepancy between the observed abundance of lithium in the universe and the predictions made by Big Bang nucleosynthesis models. According to these models, light elements such as lithium, hydrogen, and helium should have been produced in specific amounts during the Big Bang. However, when astronomers examine the gas clouds and ancient stars in the universe, they find that the amount of lithium is far lower than expected. Several theories have been proposed to explain this gap. One possibility is that stellar processes deplete lithium in the atmospheres of stars. Within the hot interiors of stars, convective currents could carry lithium to hotter regions, where it is burned and transformed into other elements. This is especially likely in older stars, which may have consumed much of their lithium. However, even after accounting for this depletion, the observed lithium levels still don't fully match the predicted values. Another theory suggests that the cycling of material through multiple generations of stars over time could explain the depletion. As stars form, evolve, and eventually expire, they might gradually consume and reprocess lithium, making it less abundant in newer generations of stars. Yet this theory fails to account for the particularly low lithium levels observed in the oldest, most metal-poor stars, which should reflect primordial abundances. A more speculative hypothesis points to early stars, known as population 3 stars, which may have processed lithium in unique ways due to their distinct properties. However, since these stars have not yet been observed directly, this idea remains unproven. The lithium problem has also led some scientists to propose that new physics might be involved. Modifications to particle physics could have influenced the rates of element formation during the Big Bang. Alternatively, the existence of unknown particles or processes could be affecting lithium production, although this remains speculative. Solving the lithium problem requires advanced observational tools, refined theoretical models, and deeper insights into the processes of stellar evolution. Understanding the nuclear reactions that produce and destroy lithium during the Big Bang, coupled with the exploration of non-standard cosmological models, may ultimately bring us closer to resolving this fundamental cosmic puzzle. In the realm of high-energy astrophysics, fast radio bursts, FRBs, have captivated the attention of researchers. These mysterious and fleeting bursts of radio waves originating from deep space are characterized by their short but intense durations. The origins of FRBs remain elusive, but their study could hold the key to understanding some of the most extreme and powerful processes in the universe. The nature of Oumuamua, the lithium problem, and the enigma of FRBs all illustrate the complexity and richness of the cosmos. While we may not have all the answers today, each discovery propels us closer to unlocking the secrets of the universe, revealing the hidden forces and phenomena that shape the very fabric of reality. As we continue to explore and investigate these mysteries, we may one day find that the answers to these cosmic puzzles are even more astonishing than we can imagine. The search for the origins of fast radio bursts, FRBs, has taken a significant leap forward, but their exact source remains one of the most intriguing puzzles in modern astrophysics. Despite the recent surge in detecting these powerful cosmic signals, understanding where they come from and how they are produced is still a topic of heated debate among scientists. Numerous theories have been proposed, each trying to explain the enigmatic nature of these bursts, but no consensus has been reached yet. One of the leading hypotheses points to highly magnetized neutron stars, known as magnetars, as the origin of some FRBs. Magnetars possess magnetic fields that are billions of times stronger than those of normal neutron stars, and it is believed that the sudden release of this magnetic energy could generate the intense radio bursts we observe. This theory gained traction after scientists noticed that certain FRBs repeat, suggesting a persistent source, much like flares emitted by magnetars. These bursts, unlike the sporadic one-time events seen in other scenarios, fit well with the behavior of magnetars, making them a prime candidate for further exploration. However, there are other possibilities that cannot be overlooked. One such idea involves neutron star mergers, where two neutron stars collide in a catastrophic event. The immense energy released during these mergers could produce short-lived but incredibly powerful bursts of radio waves. This scenario might explain some of the non-repeating FRBs, which seem to differ from the more regular bursts associated with magnetars. The variety of observed FRBs suggests that different types of signals could have different origins, possibly linked to different cosmic events. Beyond neutron stars, the universe holds other fascinating possibilities for the origins of FRBs. Some researchers have proposed that black holes, specifically those interacting with their surroundings, could be responsible for the bursts. Accretion processes involving black holes, or the merger of a black hole with another compact object, might generate the necessary energy for FRBs. Furthermore, the energetic processes surrounding supernova explosions and their remnants could create conditions conducive to producing these high-energy radio bursts. Some even speculate that interactions between ordinary matter and dark matter could explain the origin of these signals, although such ideas remain highly speculative and are not widely accepted by the scientific community. While these theories are captivating, there is one that continues to spark both wonder and controversy: the idea that FRBs could be artificial signals from advanced extraterrestrial civilizations. Although this notion captures the imagination, it remains unsubstantiated by any concrete evidence. Still, the possibility of discovering alien technologies through such signals adds a layer of intrigue to the ongoing search. Recent advancements in observational technology, such as the Canadian Hydrogen Intensity Mapping Experiment, CHIME, and the Australian Square Kilometre Array Pathfinder, have provided a clearer picture of FRBs. These instruments have successfully pinpointed the origins of some bursts to specific galaxies, many of which are billions of light years away. By analyzing the dispersion and polarization of the radio waves, astronomers can gather valuable information about the space the bursts traveled through, which provides crucial clues about their origins. As new telescopes, such as the Square Kilometre Array, become operational, astronomers expect to capture an even greater number of FRBs. With continued monitoring and enhanced observational capabilities, scientists hope to refine their models and pinpoint the sources and mechanisms behind these mysterious signals. The search for the origins of FRBs is ongoing, and with each discovery, we are one step closer to uncovering the cosmic secrets they hold. On another front, the study of intermediate mass black holes, IMBAs, presents a fascinating gap in our understanding of black hole formation. These black holes lie between stellar mass black holes, which form from the collapse of massive stars and have masses ranging from a few to a few dozen times the mass of the Sun, and supermassive black holes, which reside at the centers of galaxies and possess millions to billions of solar masses. Despite numerous detections of stellar mass and supermassive black holes, evidence for IMBHs with masses between 100 to 100,000 solar masses remains elusive. The difficulty in detecting IMBHs lies in their subtle signatures. Unlike supermassive black holes, which radiate immense amounts of energy as they pull in matter from their surrounding environments, IMBHs might not have such clear markers. This makes them harder to detect, particularly if they are located in less dense regions of galaxies or in isolated environments where there is little material available for accretion. Similarly, unlike stellar mass black holes, which often reveal themselves through their interactions with companion stars in binary systems, IMBHs may not display such obvious behaviors, further complicating the search for them. The formation mechanisms of IMBHs are still a subject of much debate. One theory suggests that they could form through the runaway collisions of massive stars in dense star clusters, but such conditions are rare, and the resulting black holes might be ejected from the cluster, making them difficult to find. Another hypothesis proposes that very massive population 3 stars, the first generation of stars that formed after the Big Bang, could collapse directly into IMBHs, bypassing the supernova stage. However, observing these stars is challenging due to their potential rarity and the vast distances involved. Recent observations have provided some tantalizing hints of IMBHs. The detection of gravitational waves from binary black hole mergers by observatories like LIGO and Virgo has opened up the possibility of finding IMBHs in the mass range between stellar and supermassive black holes. For instance, the mergers of black holes with masses in the intermediate range have provided critical data that may help confirm the existence of IMBHs. Additionally, ultraluminous X-ray sources observed in nearby galaxies may suggest the presence of IMBHs, as their luminosities exceed what is expected from typical stellar mass black holes. Future missions and observatories such as space-based gravitational wave detectors like the Laser Interferometer Space Antenna, LISA, and advanced X-ray telescopes are expected to enhance our ability to detect and understand IMBAs. These tools will provide deeper insights into the environments and formation processes of these enigmatic objects. The search for IMBHs represents a thrilling frontier in astrophysical research, and as observational techniques continue to improve, we can expect to learn more about these elusive objects and their role in the broader cosmic landscape. The true nature of dark energy remains one of the most intriguing and elusive puzzles in the vast field of cosmology. Hypothesized to be the force behind the accelerating expansion of the universe, dark energy was first identified in the late 1990s. This discovery, which came through the observation of distant Type 1a supernovae, revealed that the universe's expansion was speeding up rather than slowing down, as had been expected. Despite its significant influence on the cosmos, the exact properties and origins of dark energy are still poorly understood, making it one of the greatest mysteries in science today. Dark energy is unique in its pervasive, uniform presence across all of space. It is thought to exert a repulsive force, counteracting the attractive pull of gravity and driving the accelerated expansion of the universe. However, its characteristics remain elusive, and the theories surrounding it have become as varied as the concept itself. One of the most well-known hypotheses is the cosmological constant, originally proposed by Albert Einstein. As a modification to his equations of general relativity, the cosmological constant represents a uniform energy density filling all of space. This constant energy, often associated with the vacuum of space, generates a repulsive force that pushes the universe outward. While the cosmological constant offers a neat and elegant explanation, there's a glaring issue. The value derived from quantum field theory calculations is vastly larger than what is observed in the universe. This discrepancy is known as the cosmological constant problem, and it has led scientists to reconsider whether this model is truly the right one. Could there be something more at play? One alternative to the cosmological constant is the theory of quintessence, which proposes that dark energy is not constant, but dynamic, evolving over time and space. Quintessence suggests that a scalar field could vary in strength, potentially explaining the changing rate of the universe's expansion. However, no direct evidence for such a field has been found, and understanding its nature remains a formidable challenge. Moreover, some physicists are exploring whether our current understanding of gravity itself needs to be revised. Could it be that general relativity is incomplete on cosmic scales? This idea is explored in various alternative theories, such as modified gravity models and brane-world cosmology, which suggest that changes in gravitational dynamics might be responsible for the accelerated expansion. These theories strive to unify cosmic acceleration with other gravitational phenomena, proposing a new framework that could explain the observed acceleration without invoking dark energy as a separate entity. But even these innovative models face hurdles, particularly in providing observable evidence to support their claims. Other models suggest that dark energy might not be a solitary force at all. Some propose that it interacts with other components of the universe, such as dark matter or massive neutrinos, potentially influencing the rate of expansion in ways we do not yet fully understand. These interactions could vary over time, offering an intriguing avenue of research into how dark energy fits into the broader cosmic picture. Then there are the more speculative ideas, inspired by string theory and the holographic principle, which propose that dark energy could arise from a higher dimensional framework. These theories, though fascinating, remain firmly in the realm of the theoretical and are far from being proven. Despite the wide range of proposed theories, no single one has yet emerged as the definitive explanation for dark energy. As our understanding of the universe deepens, so too does the complexity of the questions we face. To this day, scientists continue to observe and gather data, seeking clues that will help unlock the secrets of this mysterious force. Ongoing observational projects such as the Dark Energy Survey, the Euclid Space Telescope, and the upcoming Nancy Grace Roman Space Telescope are working to map the expansion of the cosmos with greater precision. By studying the large-scale structure of the universe, the cosmic microwave background, and the behavior of distant supernovae, these efforts aim to narrow down the possibilities and refine our models of dark energy. The mystery of dark energy is far from being solved. While we have made remarkable strides in understanding the universe's accelerated expansion, the fundamental nature of dark energy remains one of the greatest unsolved riddles in modern physics. As we push the boundaries of our observational tools and theoretical frameworks, the search for answers continues. Could dark energy hold the key to understanding the deepest workings of the universe? Only time and more research will tell. What are your thoughts on dark energy? Do you believe we are on the right track, or is there something we're missing? Let us know your views in the comments below. If you find this topic fascinating, be sure to subscribe to Starflux for more insights and updates from the world of cosmology. Thanks for watching.